international mission goal. So India also approved National Quantum Mission in April 2023, which is a flagship initiative with a budget of around 6,000 crore, through which India position as a quantum technology leader in the world. So I'm not saying more because we have a very, very interesting talk from very uh, eminent speakers from ISRO. We have a expert in quantum communication from ISRO, Dr. Deepak Mishra sir. We also have faculty members in quantum metrology, quantum computing from IIT Kanpur, IIT Delhi. We also have a resource person from IIT Delhi, which is in quantum material and devices. We have from KIT Tamil Nadu. We also have an industry person from QNO Lab Bangalore. So I'm not saying much about. Let us first officially welcome you all in this event. And therefore, I wish all the participants a productive and enriching experience over the next week. Once again, I welcome you all to join this event. Thank you, sir. Next, I would like to invite our head of the department and also Dean of School of Basic and Applied Science, Professor Manoj Kumar, sir. So please address the gathering. Over to you, sir. Manu, sir. I hope.
Okay. Okay. Thank you, Dr. Divya. Honorable Vice Chancellor, Professor Shamsher, all dignitaries present here, all the heads, deans, faculty members, and dear participants, a very good afternoon, everyone. It is an honor for me to introduce School of Basic and Applied Sciences, HBTU Kanpur, to this short-term course on Quantum Technology for Innovations and Startup 2026. I extend warm greetings on behalf of the School of Basic and Applied Sciences, HBTU Kanpur, to the organizers and participants who have made this gathering possible. And all School of Basic and Applied Sciences includes three departments: Department of Physics, Department of Chemistry, and Mathematics Department. All three departments are the oldest department in HBTU Kanpur and are having highly qualified faculty members who are carry out excellent research in their area of specialization. Department of Physics offers MSc program in Material Science and Nanotechnology. Chemistry department offers MSc program in Chemical Science, and the Department of Mathematics offers BSMS and MSc program in Data Science. All three departments also offer PhD program, and research scholars enrolled in the departments carry out excellent research in their research areas. The School of Basic and Applied Sciences has been pioneered in research for last several decades. Large number of PhD degrees have been awarded under the guidance of the physics departmental faculty members and published more than 600 research articles in various national and international journal of repute. In the Department of Chemistry has also published a very good number of research articles in various national and international journal of repute. Department of Chemistry has also awarded large number of PhD degrees under the supervision of departmental faculty members. Apart from this, the chemistry department also provides testing and consultancy facilities to the industries of Kanpur and nearby areas in order to improve their product qualities. The mathematics department is well equipped with all the necessary facilities. The experienced and dedicated team of the faculty members published a very good number of research articles in various national and international journal of repute. Nearly 100 students have been awarded PhD degrees under the supervision of departmental faculty members. So all three departments are having highly equipped UG, PG, and research facilities. All three departments also successfully completed research projects sponsored from various funding agencies like CSIR, DST, UGC, etc. The main strength of the School of Basic and Applied Sciences, HBTU Kanpur, has been research and development for last several decades. So now coming to the short-term course on Quantum Technology for Innovation and Startup 2026. We are on the verge of a revolution in technology. So quantum technology, formerly formerly confined to the theoretical study, but now it is rapidly emerging as an engine of innovation spanning computers, communication, sensing, healthcare, finance, and national security. Those who are those who can turn quantum concepts into useful skills. Kindly mute yourself. Kindly mute yourself.
I think Dr. Gupta ji, kindly mute yourself, sir.
Okay. So over the past 20 years, startups have used data, cloud computing, mobile technology, and artificial intelligence to transform our environment. At present, quantum technology is on the edge of another revolution, which there is some error. So qubits, which can exist in several states at once, are used in quantum computers. Because of this, quantum systems can solve some problems tenfold more quickly than the traditional machines. So quantum computing, which solves complicated optimization chemistry and artificial intelligence problems, quantum communication, which explain ultra secure data transfer using quantum and encryption, and quantum sensing, which classifies extreme precision in navigations, medical sensing, and climate monitoring, or the main areas of quantum innovation. So quantum technology is not come to replace traditional computers, rather it is here to improve human capability. So let's learn, innovate, and propagate ourselves to be a part of quantum revolution. So thank you very much. Over
Thank
to
you,
Dr.
sir.
Divya.
Thank you, sir. Thank you, sir. Thank you very much, sir. Now I would like request Professor Jiten Pashkar, Dean, Incubation Hub, to sir please address the gathering. Over to you, sir. Bhaskar, sir.
Thank you, Dr. Divya. Good afternoon to everyone, and Honorable Vice Chancellor, sir, and all deans and dignitaries and speakers, experts from industry and participants. So we, on behalf of Teen Incubation Hub, I welcome you all in this course. And the story started for this course, quantum on the quantum issue. We visited our this ISRO on December 29th and 30th with the motivation of our Honorable Chancellor and the Governor of Uttar Pradesh and our Honorable Vice Chancellor, sir. So for observing or for having some kind of a experience on what is happening at high level of R&D in India. So we got opportunity, and our team members, students got opportunity along with all the other technical universities, faculty in startups. So we could observe there that India is moving ahead, and for this we are requiring a new kind of new dimensions, because this era is changing from the very slow computing or whatever the computing status we are having. So right now we are moving forward for our recent new demand in the case of communication for our satellites, for our aerospace. So everything for our environment related issues, for modeling issues of our geographical situations or our boundaries. So we could get the experience, all the kind of thing there. And same time also, this is a really demand where we should have this technology to overcome our previous obstacles. So definitely technology is moving ahead. So in all the area, the technology is growing. So we have to be cope up with this all the situations. So in view of that, we planned after returning from their visit, we planned this is I think this is a first program. And Dr. Divya Somvanshi, I congratulate her for moving, for taking a step as a leader for planning this activity, and we, Dr. Manoj, and our sir, Vice Chancellor sir, has motivated us for doing a great program on this issue and taking this step first. So definitely we contacted all kind of all speakers, and especially if from the ISRO, Dr. Mishra is there, and other faculty members and other industrialists also we are having. So with this program, and our in the HBTU Kanpur or in UP also, that we will create a awareness for this quantum technology, and how this startups can be benefited, or how new startups can think in this area of making new startups, starting this with the help of the for completing the demand in communication and all the demands I have already discussed, with the core technology in material science and the manufacturing also. So most of the things are in cybersecurity, communication, all are the requirements. And these who can serve this area and who can contribute in this area, these are the mathematics people, the manufacturing and material science core. So that was and also the manufacturing, how we can minutely make a compact our circuits, our designs for our electronic based designs, for making this a very small and at nano level devices. So it will payload terms, it will be very light also, and giving you fast performance. So finally, because payload is going to the very costly affair. So we can make our launching cost of any satellite at a very low cost, and same time or we can have a extra extra level, or you can say a high level in the world scenario in this area. So I thank you all organizing committee members, and thanks our Honorable Vice Chancellor for supporting in all means for conducting this ceremony for this course, also short-term course on quantum technology. So thank you all so much.
Thank you, sir. Thank you, Bhaskar sir, for saying for addressing the gathering. Now I would like to invite our guest of honor, Honorable Vice Chancellor, HBTU Kanpur, Professor Shamsher sir. Sir, please address the gathering and motivate us. Over to you, sir.
Thank you, Dr. Divya. Thank you very much for inviting me. Respected resource persons, especially Dr. Deepak Mishra from ISRO, from other
Connection a little bit issue. Let us wait.
Okay. So I want to brief you some little bit information, as there is some connection issue. That HBTU Kanpur is having this incubation center here established, and we are recognized by MSME and as well as Starting UP. And so we have 24 startups here in all streams, from healthcare to the agri-tech and also in manufacturing also. So we are we are motivating our students, and as well as same time other nearby people for doing something in this startup area, and can employ themselves, and also make a situation for increasing employability also. So if anyone in this gathering is interested to know more about our incubation center, our facilities, or our areas. So they can contact us in better way. And Dr. Divya is also here for taking these issues in this area, quantum technologies. Yeah. So I think
there is some connection issues from sir side.
So if any other speaker or program, we can we can reschedule it in the next stage. Our sir can join me, I think.
I think.
Or we
Okay,
can
sir,
talk
I think let us just call him maybe.
Just I am calling her. I
Okay,
am
okay.
calling. We can wait few minutes. I think phone is also busy.
Maybe he got some call from very important call. That's why he switched. Maybe just wait. Participant, we will wait for our honorable Vice Chancellor, sir. Sir, already.
Hello, Divya?
Yes, sir. Yes, sir. Please, sir. We are waiting for you.
I was just reading something and I was informed that there is no voice. So you could have immediately called me. Okay, so good afternoon again. Good afternoon, all of you.
Yes, sir.
respected resource persons, Dean of the University, HOD, respected faculty members from the department, the industry experts, leaders, my dear researchers, students, and young innovators. Good afternoon again. I'm really happy to be here with you in the inaugural session of short-term course on quantum technology for innovation and startup 2026. I congratulate the organizing team for choosing a theme that represents not only the future of science and technology, but the future of national competitiveness, security, and entrepreneurship. Dear friends, quantum technology is no longer a subject of distance laboratories or theoretical physics alone. It is rapidly moving into the real world applications like impacting computing, communication, sensing materials, healthcare, finance, and national security. Countries that master quantum technologies today will define the global leadership tomorrow. I'm happy to note that in the Union Budget 2026-27, the Government of India has continued strong support for emerging technologies, particularly quantum research, deep tech startups, cybersecurity, infrastructure, and indigenous innovation ecosystem. Provisions under the National Quantum Missions enhance funding for R&D, startup incubation, skilling programs, and industry-academia collaboration. Clearly signals that India is serious about becoming a global hub for quantum-enabled technologies. This course aligns perfectly with the national vision. Dear participants, quantum technologies have transformational applications. Quantum computing can solve problems beyond the reach of classical computers, optimizing logistics, drug discovery, climate modeling, and financial systems. Quantum communication promises ultra-secure network through quantum encryptions, strengthening cybersecurity and data sovereignty. Quantum sensing and meteorology can revolutionize navigation, medical imaging, space research, and precision manufacturing. However, with the great power comes with the great responsibility. As we train innovators and startup founders in such powerful technologies, we must emphasize the ethical use of technology. Quantum tools must serve humanity, not undermine the privacy, destabilize systems, or widen inequality. Cybersecurity responsible innovations, transparency, and respect all societal values must be integral to every technological breakthrough. Equally important is discipline. Discipline in learning, discipline in research, discipline in experimentation, and discipline in entrepreneurship. Quantum science demands patience, rigor, collaboration, and humility before nature. There is no shortcuts here, only sustained efforts, integrity, and curiosity. To the student and startup aspirants present here, I would like to say, dream big, but build strong foundations. Use this course not only to acquire technical knowledge, but to develop a mindset of innovation, ethical leadership, and national responsibility. India needs quantum scientists who are also good human beings and responsible citizens. I am confident that this program will ignite new ideas, inspire startups, and contribute meaningfully to India's journey towards a secure, self-reliant, and innovation-driven future. With these words, I formally inaugurate the short-term course on quantum technology for innovation and startups 2026. I wish the program great success and all participants a truly enriching learning experience. I'm also thankful to the Department of Physics for inviting me to inaugurate this FDP program. Thank you. Thank you all of you. Jai Hind.
Thank you so much, sir, for your nice word and motivating us. Now, I would like to invite Dr. Abhishek Kumar Gupta, sir, Associate Professor, Department of Physics, to present vote of thanks, sir. Over to you, sir.
Yeah. Thank you, Divya. Am I audible?
Yes, sir, you're audible.
Oh, thank you. Yeah, good afternoon, everyone. As we are concluding this inaugural session of 1 week short-term course on quantum technology for Innovations and Startup. I, on behalf of Organizing Committee and Department of Physics, HBTU Kanpur, extend my heartfelt gratitude to all who have made this event a success. First and foremost, I wish to extend my profound and deepest thanks to our Honorable Vice Chancellor, Professor Samser. Sir, your visionary leadership, constant encouragement, supports, motivations, and guidance always remain the driving force behind our academic pursuits. Your leadership is truly a source of motivation for the entire HBTU family. We are truly grateful for your presence today. Your words have set a powerful and inspiring tone for this entire course. Thank you, sir, for your steadfast support and for always inspiring us to bridge the gap between science, technology, innovation, startup, and entrepreneurship. My sincere appreciation goes to Professor Jitendra Bhaskar sir, Dean Incubation, for his unwavering supports and motivation always. Thank you, sir. We are equally grateful to Professor Manu sir, Dean Basic and Applied Science and Head of Physics Department for his throughout guidance and planning of these programs. Thank you very much, sir. And we are grateful to the convener of this program, Dr. Divya Somvanshi, for her support and all the preparation for the smooth conduction of this event. Our gratitudes extend to the distinguished guests and all the invited speakers present here. I hope you all will set the stage for the next week ahead. I also thank all the faculty members and dignitaries present here for their active participation. I special mention to our research scholars for their diligent work in managing this event. Their hard works and team spirit have been vital to smooth conduction of this program. So thank you. And finally, to our participants, your enthusiasm and participation make this initiative more meaningful for us. Thank you all for being part of this inaugural ceremony. We are now ready to embark on a journey of this 1 week course, and I wish everyone a very productive and insightful week ahead. Thank you very much. Thanks.
So much, sir. So now we are concluding the inaugural ceremony and moving towards our keynote talk. So our keynote speaker is Dr. Deepak Mishra from Indian Space Research Organization, ISRO, Ahmedabad. So let us, sir, I hope you have joined. Mishra, sir?
Yeah, Divya, good afternoon. I have joined and hopefully
okay, good afternoon, sir. Good afternoon.
Good afternoon. Hopefully my voice is also coming perfect because I saw
yes,
a lot
sir,
of
yeah.
research.
Yes, sir, it is coming perfectly, sir. So first, all the participants, a very good afternoon all to all of you. First, let us brief the profile of Dr. Deepak Mishra. Dr. Deepak Mishra is a scientist, engineer G, and head of navigation payload electronics division at Space Application Center, Indian Space Research Organization, ISRO, Ahmedabad. He has received his PhD degree from IIT BHU Varanasi on the topic Joint Source Channel Coding for Deep Space Application in the year 2012. He received his MTech degree in Communication System Engineering from the Department of Electronics Engineering, IIT BHU in 2003, and B degree in Electronics and Communication from Government GB Pant Engineering College, Uttarakhand, India in 2001. He is associated with SAC ISRO since the year 2003, and during this tenure, he has been involved in various subsystem development of various ISRO projects. Currently, he is involved in the design and development of payload for NAVIC system as an associate project director in technology demonstration payload and as a focal person communication module for Gaganyaan project. Very good. He has more than 85 papers in various international journals and conferences. He has also delivered invited talk in international conference at Tokyo University, Japan in 2016. He has 6 patents and 3 copyright, including 1 US patent to his credit. He is the focal person for signal processing module of postgraduate course of United Nations SATCOM course and faculty member in the navigation system course. He is a fellow of various academic institutions like IIETE, IEASI, and ISSE. He is appointed in the board of advisory members of MapWorks India. He is also an ISO 170242012 certified project manager. He is approved PhD guide ISC Bangalore, IIT Gandhinagar, Gujarat University, and Nirma University, Ahmedabad. Thank you so much, sir, for joining us today. We heartily welcome you, sir, to this our 1 week online short-term course. Over to you, sir.
Yeah, thank you, Divya. First of all, let me give you the big thanks for inviting me and I would like to put my thanks and gratitude to Honorable Vice Chancellor HBTU. I know, sir, that you are there for this with our
Yeah,
VP Governor.
and yeah, Dr. Deepak, I really appreciate and really admire your facilities available in your SACS center, and really we enjoyed your visit. And then I came to the university and discussed with physics department to conduct some program in association with the SAC. So I'm really happy and thankful to you that you have agreed for the invitation of our physics department, and your experience certainly will benefit our faculty and the researchers. And really thankful to Dr. Deepak. Thank you very much.
Yes, sir. Being a native state of UP, I belong to basically from place Varanasi. So it's my duty to that for the state. If I can contribute by any means, it's my. And since I'm belonging to ISRO last 22, 23 years, so we have a very good, I can say the detail what ISRO is trying to do and what is our future plans. So basically, in today talk, what I am trying to say that in the quantum, we are also not very old. We identified this potential technology, I think, 8, 9 years back, and we started investment on that on very small scale. But today, now we are at the verge of country first quantum satellite is about to ready, and maybe in February, March, we have a first launch of India first quantum satellite. And even in this attempt, if we are successful from the world point of view, we are second to China in the world who has basically launched the quantum satellite and real-time quantum key distribution we are going to demonstrate from geolocation orbit. So that will be the very big achievement for India in terms of technology, in terms of things. But as our current government is very much behind the technology, so we are not going to stop here. As government knows that we are very close to launch of our first satellite, they have approved 2 operational satellite of the quantum, which we are scheduled to launch in next 2 years. So that is the way we are getting a fund, as you mentioned, is correct. Full, basically full funding we are getting from government for the advanced R&Ds particularly. And as you know that ISRO is basically made for the delivery of the systems. We are not stopping just to put the things. We are basically at the end. It should be useful to common people requirement, like our defense users or the common people. So consider, So considering all this aspect, basically I am fortunate enough that I am a associate project director for this quantum satellite. And since from December, I was in Bangalore for integration of this quantum payload with the technology demonstration satellite. It has been successfully integrated, successfully tested. Now satellite is in the final round of testing, and then we are shipping this satellite to SHAR for the next PSLV launch. And we are very much sure that in the first attempt itself, we are going to demonstrate real-time quantum key distribution from the satellite to ground.
Very good. So our best wishes for your endeavors, and we hope that you will be the India will certainly be successful in your endeavors. So correct, please, thank you very much, sir. Thank you.
Yeah. So now I will share my slide, Divya. Just confirm whether the slide is visible. Let me share my PPT first. So slide is visible, Divya?
Yes, sir. So it is coming.
Yes, it's visible,
perfectly.
Yeah. Okay. So thanks. Again, good afternoon to all. So let us go for the journey of quantum communication, particularly for the satellite communication. So as a lot of speakers before me in the inaugural session, they talk about the importance what government is giving for this quantum things. So today talk, basically I'm basically going to cover one area of the quantum where government is putting lot of effort. And as a part of ISRO, we are also trying to put lot of effort to make it happen. So currently my talk basically covers what we have done in the past, where we are right now, and what is our future plan. And as a part of academia, what I request is please go through that the technology where I will basically call for demand to major upgradation. So if you are think that you can participate, you are always welcome for that. And in fact, if you go through our response basket of this year, I think the date is also extended up to February 15th. You can see there are few projects where we are basically looking for some quantum collaboration. So if you think that you can collaborate, please, you are most welcome. Now coming to the my talk. So slide is changing, Divya, confirm?
It's changing, Divya? Sir.
Yeah,
yes,
yeah,
sir,
okay.
it is changing. It is changing.
Okay. So basically, I will try to cover the quantum technology for the satellite communication. Actually, if you talk about the quantum technology for the satellite communication, you need to discuss slightly about the optical technology as well, because this quantum and optical will go in tandem together. And ultimately, in satellite communication, why we are introducing these two technology, basically call for a high throughput satellite. So I will not go in detail about the high throughput satellite because the main agenda is the quantum technology. But I will try to showcase some glimpse where this technology will going to fit in and what purpose for that. So coming to the importance of this quantum technology, as previous speaker mentioned that the government of India has identified 9 key missions for our future enable emerging technologies, and out of which quantum is also one of the important milestone to discuss with. And basically, if you see that why this is getting so much importance in terms of national security, it is more important. So what are the areas where basically in quantum also we can invest is basically quantum computers, quantum communication, new materials for the quantum sensor, and quantum cryptography. So these all areas are independent, and they are basically part of umbrella coming in the quantum frontiers. And in fact, if you see the globally also, the 2022 Nobel Prize is given to these 3 gentlemen. They are basically working on entangled photon source. So as a physics person, I can say the entangled photons are the most beautiful things, which is basically part of any physics where 2 photons, even though they are apart, but they will behave like a identical single unit type of things. So these gentlemen, 3 gentlemen worked on this entangled photon source, basically to check the violation of Bell inequalities. So it is basically what I mean to say is that there is a globally also people are now seeing the importance of the quantum. And even this year physics Nobel also is going for the quantum work only. Basically, these 3 gentlemen worked on quantum tunneling. And basically idea is to understand the different quantum system like quantum computers, quantum sensors, and quantum encryption. So I think this is the most noble are nowadays people are working on quantum, and this way it's going on the quantum side. Coming to the quantum communication, where I am going to talk more, is basically there are 2 ways to basically transmitter and receiver. And what is our idea is to transmit the message from transmitter to receiver securely. So before the quantum, this idea is basically we do the encryption, RF encryption or some type of public channel encryption technique. We are using it. But you know, recently, a lot of hacking event is happening, and the data security is one of the key missions for the government also. Even for the defense user, the data transmission, critical data transmission securely is the key challenges. So in order to handle these things, this quantum cryptography or quantum key distribution, we call as QKD protocol. So quantum key distribution is coming into the picture. And right now, my team is working on this QKD protocol distribution only. So what is the biggest advantage once we are using this cryptography technique using quantum? So answer is theoretically unhackable. So what I mean to say, if you are going to encrypt it by the quantum key, the receiver will receive a secure communication. If any eavesdropper is coming in between, the receiver will came to know that there is a hack happen in between, and he can discard the message. So what is the biggest advantage using quantum key distribution is that is theoretically unhackable. Means no one can hack. And even if it hacks, then the receiver will came to know that it's been hacked by the key has been or the message has been compromised. So what are the advantage once this type of unhackable technology we can incorporate? So basically, it will be very useful for the banking industry, finance industry, credit card industry, where a lot of OTPs are shared for the financial transactions, government and defense industries, and protecting high secure sensitive data, particularly for the defense user or remote data centers. So there we can incorporate this quantum key distribution so that it can be secure. The last thing, which is also very critical, you know, in the NAVIC satellite, NAVIC is basically Indian navigation system, where we basically deriving 2 type of services. One called general services, we call SPS service. Another is called restricted service, that is for our defense user. So defense user messages are typically encrypted. So the current technology, what we are incorporating in NAVIC satellite is the RF-based encryption system. Although it is slightly compromised in the security system, because as you know that the classical RF encryption system can be hacked and it can be decrypted also. So in future, our plan to migrate from this RF-based encryption system to the quantum key-based distribution system. Why it is so important? So earlier, what happens? This key distribution system of NAVIC is manual in nature. So the soldier which is sitting in Siachen Glacier, the key earlier going manually. So it will roughly take 1 week to change the key. So that is the not a viable solution. Then in NAVIC second generation satellite, we migrated from RF key distribution system. Although it is quite secure because the QKD, the encryption protocol is indigenously developed and it is thoroughly tested, but still there is a remote possibility that it can be hacked. But in future, we are going to migrate from this RF key based distribution system to the quantum key based distribution system. So theoretically, it becomes unhackable. So that is the areas where we have identified for this quantum key distribution. That's why we are migrating from classical encryption technique to the quantum key distribution system. Then the question comes, why we are going for this satellite-based quantum communication? So as you know that if we put 3 geo-satellite means from ground, it is roughly 36,000 kilometers. So virtually satellite becomes stationary with respect to the Earth. Then what happens? Theoretically, if you put 3 geo-satellite across the Earth, you can cover the whole globe. So that is the biggest advantage, means only few satellites, it can cover the whole globe. So if you go with the quantum network distribution, so either we have a two option. One, we go with the optical fiber based solution, or we go with the satellite based communication. So optical fiber, if you think about just to cover whole India, even that to Siachen to Kanyakumari, it will take a long time and it's not a viable solution. So the better idea is to make a satellite as a node centers, and then internally within the region wise, you can distribute the optical fiber. So this is the hybrid solutions which government we have proposed, and I think it has been approved by Government of India. So that's why we are now putting a basically satellite-based optical communication system and make a good infrastructure for the country so that it can be practically used for various applications. So who are the other countries which are basically participating in this satellite-based quantum? They are the two major countries like China and Japan. They have initially successfully demonstrated this quantum experiment from satellite to ground. So my talk initially will basically try to just give you the flavor of worldwide development, and then we'll come to our India program. So these basically worldwide, if you see in terms of satellite communication, it has started in 2005 timeframe, where people just started with some initial development of quantum key distribution system. Here I like to first highlight mostly the satellite communication using quantum is basically made for the secure communication only. That is the main purpose for whole of the objective of the any one nation you can take it. But I will just emphasize on 2021 and 25 time frame where it has taken more pace for things, where UK, China, and Japan, and even India has just initiated 2 quantum programs for the free space quantum communication. Before that, some small experiment has happened in 2011 to 15 or 16 to 2022. I will just showcase you some important experiment worldwide. This is the MECUS program by China Academy of Science, and basically they actually this key distribution also work on some certain algorithms. So one of the algorithm name is BB84 protocol, and another is called BBM92, which I will cover later on. And basically in this experiment, they have demonstrated this quantum key distribution from 600 kilometers to ground, and they worked on 850 nanometer and 810 nanometer, and you can see the key rate for BBM84 is 1.1 kbps to 10 kbps, and BBM92 QKD distribution they have demonstrated at less than 1 bit per second key rate. So these are the hardwares for this them, and they have successfully demonstrated from LEO orbit to ground. So these are the some their payload diagram and photographs of the product. Coming to the other things, in 2017, Japan has done some experiment. They have basically trying to this BBM92 protocol from LEO orbit to small optical transponder, and they also use around 800 nanometer, and they have put 10 megahertz broadband pulse. So they also got a small success on this. In 2019, Singapore basically this entangled photon source. We have done a lot of experiment at ground, but in 2019, Singapore has sent a small CubeSat satellite, And they wanted to see the behavior of entangled photon pairs, particularly in space, because before that, nobody has seen the behavior. So they are not sending anything ground. They are basically trying to test the loopback mode of this entangled photon BBM92 protocol in the satellite itself in the loopback mode. And they got the data and they said that there is no much difference even you do at the ground or in the satellite. So these are the important experiment in the things. Now coming to, I just showcased few important experiment which people had done it. Now coming to our Space Application Center, SAC. So SAC has basically three important pillars. One pillar is known as communication payload and microwave and optical payload. Another is called as remote sensing payload technology, where also some microwave and optical payloads are there. And then the application area. These are the three important pillars where people in ISRO and SAC particularly divided. Now, once we think about that, we have to introduce the quantum technology. So we identified two things. So one is this quantum communication, which will be fit in this communication payloads area. Another is the quantum radar, which we were trying to fit in with this remote sensing payloads and optical payloads. So once we identified these two pillars, will be the basically we try to invest in this communication payload and remote sensing. We need to first identify what are the technology required for, because this is not the things which we are doing since last past. So these are the few things which we identified during the development, like quantum transceiver we required, quantum receiver, timing and synchronization, microwave photon source, receiver technology we required. We required a PAD technology because this quantum source or receiver will put in the satellite. So it need to be synchronized with the ground terminals. So pointing acquisition and tracking technology using optical, we need this technology. Then ultimately this photon will pass from satellite to ground through atmospheric. Then the atmospheric modeling is required. And obviously at the last, there must be some protocol exchange mechanism need to be developed so that we can exchange this, we can do this quantum communication. So these are the new niche areas which we identified. Once we identified that these are the things are required to demonstrate this quantum technology. Now coming to the basically baseline technology, what are the baseline technology which we required for this? So we required a basically quantum receiver, quantum transmitter. So like single photon source based things, entangled photon based source, time tagging and synchronization. So basically we need to particularly time tag the photons which we receive at the ground. So basically NAVIC based synchronization we identified, then time to digital converter. Then as I mentioned that the protocols like BBM84, BB84 protocol, BBM92 protocol, and any other new protocols which can be incorporated in our design, we need to consider that part. Then the telescope part with the PAD system. So we need to develop a ground system with the complete telescope, and then the onboard we need to put this quantum acquisition tracking mechanism to track the satellite with respect to the optical ground terminal. And obviously atmospheric channel modeling, which I discussed earlier also, is the required for. And the microwave photons quantum source is also required. So these are the niche technology, baseline technology, which we identified as a requirement. So if you talk about the like system level technology which we developed, so basically we developed into this BB84 protocol, and initially we demonstrated in free space within the ground itself within 300 meter with aerial distance of 300 meter, and we have validated this BB84 protocol, quantum NAVIC based synchronization technology, all these things. Because before putting all this satellite in the satellite, we need to validate all these things. Otherwise, directly going to the satellite is most challenging thing. Then entangled photon source based also the protocol we validated in free space, and then this NAVIC synchronization, all these things we have validated. Then the QKD protocol with the moving platform. So ultimately, once we put this quantum technology on the satellite, it will be like a moving platform. So before going to the actual moving platform, we have put in this QKD link on the like drone and validated this PAD system, because this is the most sophisticated technology which is required for any quantum communication from the satellite. And then this polarization compensation due to the moving scenario. So this we have basically done with lot of experiment at our SAC campus with the drone, and try to see where we are lagging and what need improve, call for an improvement. So a lot of iteration has happened, particularly in this QKD protocol. And then based upon that, the confirmation what we got it, we configured two payloads. One is called Quant ESS payload, where we try to see this BB92 protocol loopback mode similar to Singapore types of satellite in the space and check the performance, all the other components. The biggest challenges what we face during the development of these payloads are the availability of the component, because these are the niche technology and very few vendors in the world who can give you the space qualified worthiness component, because we cannot fly with the commercial component. The component reliability, the harsh environment of the space, we need to particularly go for more ruggedized component. So availability of such component, particularly in this technology, is very less. So something we have developed in-house and something we discuss with the vendor and develop for our own. And then as I mentioned, the last payload, the TDS payload, where I am working for, we develop basically we proposed a full-fledged quantum payload where all the major protocols will be tested in satellite from geo orbit. So I will more talk about this TDS payload later in my slides, but I was just trying to say what are the things which we have considered. Now coming to this optical ground station. So we also identified optical ground stations for the satellite tracking. In fact, one optical ground station in our SAC campus is already installed, and it has all the facility to track the satellite. Two more optical ground stations we are under development. One is at Mount Abu, another is in Leh, Ladakh. And once these three ground stations will be ready, we have our ground readiness will be fully complete. And apart from that, we are basically more toward the technology demonstration also, because this is the basically first design which we have developed. But in future, we need to miniaturize, because in space, every kg of mass will call for a huge cost. So we need to reduce our mass, size, and volume to reduce, and more optimized payload will be planned in future when the operational scenario comes. So in a single slide, if you ask me what the things which we till now have achieved, is basically we did this demonstration of QKD protocols in 300 nanometer free space. We right now working on two payloads, which one is called as Quant ESS payload and QTDS payload. In space segment, we have now full-fledged quantum program, which is based on QKD based ground system. Also, as I mentioned, that one ground station is ready, and few more ground station, two more are under development. Apart from that, as I mentioned, that we need to optimize our hardware for future requirements. So integrated photonic circuit, where a lot of optical components will be integrated on a single chip. So integrated photonic development is going on, and at the end, we'll go for the ASIC development of the quantum components. So these are the technology point of view. Now I will go through some important experiment which we have demonstrated till now. I think this is the first time in the India we have demonstrated 300 free space quantum QKD demonstration. So in SAC campus, we have two buildings which are aerially 300 meter apart. One is called building number 38, where our optical transmitter is there. Another is building number 22, where our optical quantum receiver is there. So we do basically this weak coherent pulse BBM 84 protocol demonstration from one building to another. These buildings are line of sight, and these are the few transmitter. Left side you can see that there is a quantum transmitter, and right hand side you can see there is a quantum receiver. So we developed this complete hardware to test the first time. In fact, in the ISRO also first time we had started this demonstration based on our understanding. Although initially we got lot of iterations to basically understand the protocol. Once we understand, then we started implementing in hardware. And then in March 2021, we did the first demonstration. And this is actually basically what are the silent features which we got it in this. This is, I think, India's first two-way secure quantum video demonstration. We have done it. It's based on NAVIC enabled synchronization. And we basically demonstrate in terms of ease with developer. We can emulate that key will be compromised and it can be detected at the receiver end. And we basically did the secure key data rate around 300 kbps with Q bar of less than 3%. And it's indigenously developed all the hardware. And once we did this demonstration, it is widely publicized across the India. And these are the few, I think, cut out of the papers where this demonstration has been discussed, that it is the first time in the India we did this demonstration of the quantum free key distribution over in free space. But we didn't stop here, because we know there are other challenges also will come. So after 6 months after this experiment, we again go for the same setup, but this time we changed the protocol and we migrated from single photon set based quantum key distribution to entangled based photon key distribution. And this time we go for the again secure text and image encryption and decryption, two-way communication. This time our Q bar rate is slightly less because entangled photon by inherently has a slow data rate. So we achieve around 2 kbps with Q bar is less than 10%. And this time also we demonstrated this BBM92 protocol. All other hardware are remain same. Only the protocol we migrated from BBM84 to BBM92. And this is also on the, as I mentioned, the same two buildings, only thing the protocol has changed. So if you compare with these two experiment which we conducted in 2021 in March and November, so in both the cases, the most of the things are means the hardware remains same, only the protocol and some things are changed. So this is the just a one compare slide which we have demonstrated in March and November, where we got different key rate based on the our protocol, and these two important protocol we have got a grip after this demonstration. And these are the few results which we got during that experiment. You can see that this image is encrypted with the quantum key at the receiver end. We decrypted the things. Similarly, some other also. And our ISRO chairman was there that time when we do this demonstration. So we catch him his image as well and do the encryption and decryption at the receiver end. So these are the some few snapshots. Now coming to the, apart from these two key important distribution, as I mentioned that we have identified other areas also for the quantum. So we gone for some other experiment also. So we configured two payloads, as I mentioned earlier. We initially configured two payloads. So one of the payload name is Quant ESS payload. So in this payload, basically it's a loop back mode, and basically what we are trying to demonstrate is basically entangled photon source based. We want to see the behavior of this photon in the loop back mode in the space. And this is not a dedicated satellite. It is part of PSLV fourth stage of PSLV C55, where we want to demonstrate this experiment. But actually what happens during the thermovac of this payload, we got some glitch and we got some degraded performance. So after that, we withdraw this from PSLV C55. And right now, we are basically trying to debug what is the issue, why it is getting degraded in thermovac. So still it is under development, and maybe the next PSLV, it will be again part and parcel of onboard PSLV fourth stage. So before going to this, so these are the few hardwares which we developed for this Quant ESS payload. You can see there is a EO model, ELX packages, DVM hardwares which we developed, some piezo drive mechanism, film mechanical actuators which required for. So these are the typical mass and dimensions which we develop for this Quant ESS payload. Right now, this complete payload is integrated, and we are just seeing why it is being degraded. So before that, actually, what happens? We got one opportunity to having a full-fledged quantum payload. So we started working on that direction first. So this is the satellite which is basically called as Technology Demonstration Satellite TDS-01, and it is scheduled to launch in March first week or February last week, where basically this is the, I think, country first full-fledged operational, means all aspect operational, although it's a technology demonstrator. Basically, we are going to demonstrate onboard quantum random generator, quantum cryptography, optical beacon link connection from satellite to ground, and QKD demonstration. So it is a full-fledged operational quantum satellite where we are going to demonstrate real-time QKD distribution from satellite to ground. So this is the payload block diagram. Basically, it is work based on BBM84 protocol, and we have full-fledged quantum transmitter and quantum receiver on board. We have a supported optical, you can see there is an optical chain is sitting, and there is a RF chain is also sitting. I will tell you how this whole payload will work in space. So this is the full-fledged operational payload which we have developed now, and it has gone through all the testing. Unfortunately, this time we didn't get any anomaly in the payload, because based on our Quant ESS experiments, we came to know what are the root causes for the which basically create the degradation. So we have taken care in this design, and within 1 year time frame, we have developed this full payload. And these are the few photographs. You can see this is the, I will show you the exact photograph. This is basically our quantum head assembly. And this is our electronics packages. These are the few actual photographs of the developed model. So apart from that, I will go later on this payload, and I will show you some results also. But before going to that, I will show you, apart from that, we are developing some more advanced photon quantum based basically hardwares like this quantum dots, optical cavity based things, avalanche diode based detectors. Future also, as I mentioned, that we are going for some right, currently whatever the hardware which we are developed for this TDS payload are discrete in nature, means all the optical are in discrete component based design, but in future we are trying to integrate all in the single chip, and basically we'll make a single photonic chip where all these discrete devices will be part of integrated chip. So this development is going on in parallel to what payload right now I am talking about. So these are the few developments. Apart from that, like as I mentioned, another pillar is quantum radar. So for the quantum radar also, there is a separate team who's working on this direction. So basically, they are working on this quantum dot based detectors, quantum memory, time to digital converters. So whatever the technology is required for this quantum radar, we are developing in-house for in SAC for required for. Now coming to our plan, which means where we have started and where we are. So we, as I mentioned, we didn't do quantum very long time. We started, in fact, in 2018 time frame where we identify the potential of quantum technology. So we started our R&D in 2018 time frame. We first developed our quantum lab in 2019, 2020. We did this lab development and whatever the hardware associated required for this quantum communication. And previous slides, like we did first some experiments in 2021 where we have demonstrated this QKD protocol in 2 modes. Then we migrated from 2021 to make it happen from satellite. So we tested in moving platforms in 2020, 2023. We then started investing on this quantum ground stations, because before that we cannot launch any satellite. So these 2 years we have mainly focused on our quantum ground station development. And then 2020, 25, 26, we are basically going to launch a satellite with the readiness of ground station. So this is the journey which we have done, I think 6-7 years, where all the new things we develop one by one. And then now we are in slightly advanced stage where we're going to launch our first quantum satellite. Now, apart from that, what is our future program? Before going to our current satellite detail, so that has been divided in 2 segments. Actually, once we are ready with this QTDS satellite, TDS satellite of quantum, government immediately approved our 2 operational scenarios. So in the first operational scenario, we are going to launch 2 LEO satellites, and there is a basically demonstration between 2 satellites, and then from LEO to ground. So this is called a LEO to LEO ISL, and then from LEO to ground optical communication. So this is the first part where our part 1 will go in operational scenario. And then again, I mentioned that we have a 3 OGS station plant, one at Ahmedabad, one in Mount Abu, another is in Ladakh. So that way we'll do first operational scenario. After that, we'll again going to launch one geo satellite, where it will be basically after this launch of geo satellite having an optical terminal on board. Will demonstrate geo to LEO inter-satellite link, then LEO to geo to ground. The advantage of geo satellite having on board that it is always visible to our OGS station. So anytime data downlink is required, particularly in war type of scenarios where data availability with respect to time is very critical. So we'll have the luxury of geo satellite, so that anytime whenever the LEO satellite capture the data, they transfer their data from LEO to geo, and from geo to directly it is available at our OGS station. So that's why we in part 2 will put a geo satellite on board, and there our basically wish is to have a demonstration of LEO to geo, geo to ground station. And once this platform is ready, we are full-fledged ready with this opto-quantum communication link for the defense user as well as the public user. So these are the 2 operational scenarios which we are going to basically complete in next 2 to 3 years after the launch of this quantum satellite. So these are the block diagram which we have proposed for our future quantum satellite, where basically weak coherent pulse based photon source will be there, entangled photon, both will be there on board. We have a NAVIC receiver on board, we have a SSR recorder on board, RF transceiver will be on board, and all the protocols type like optics and telescope which is required for this quantum and optical communication will be part of onboard satellite. So this is just a overall block diagram which we have planned for our future opto quantum satellite. Now coming to the optical ground station, you know that after launching a satellite need to be tracked, and then only this quantum distribution will happen. So for that, we required a very niche technology, PAT-based for pointing acquisition and tracking based optical ground station. So this is the photograph of our OGS station at SAC Ahmedabad, and there we have deployed all this hardware to track any LEO or GEO satellite from space. Similarly, we have planned 2 more ground stations, one at Mount Abu, another is at Leh Ladakh. So these 3 ground station, you may ask why these 3 locations. So we have done the extensive survey of these locations, and based on our analysis only, we have selected this ground station. So I will just cover first what are the why the required for these 3 OGS station, and then on what basis we have selected. So basically, these 3 are separately apart from each other, and they will be connected through our classical RF link also, so that any communication between required and any availability of any OGS can basically taken care by 3 OGS. So that's why a 3-way redundancy is there. Second thing, due to what type of scenario, suppose any OGS is get down by enemy, we have a another OGS who can take over of this part. So these are the few photographs of the OGS. And as I mentioned, we have not only just selected randomly, we done the extensive survey of these sites, and what we find out, there is a cloud free, because this optical communication required a cloud free, and we found out around 62%, this Mount Abu, Ahmedabad around 57%, and Leh around 21%, Hanley about 62%. So based upon the cloud free state availability, we selected these 3 basically cloud stations for this OGS station. So basically, if you talk about the satellite QKT protocol, so our wish is that there will be 2 LEO satellite, 1 GEO satellite, and these 3 OGS will be there. And these 2 protocols will operate on basis of requirement. Like one scenario could be like BB84, another is called BBM92. So these 2 protocol will be operated based on, and then there will be a ground QKD protocol, optical fiber based distribution system like this. So this is the basically our ultimate wish, where this ground station will be connected to our node through the various other nodes which are connected through the optical fiber links. So this is one terminal network. This will be the network B, where other optical ground stations also connected through this fiber optics. And finally, it will connected through satellite to other optical OGS station, and then there again fiber optic network will be there. So this is the integrated network satellite plan, which will be approved by Government of India, and now we are working on this direction. Now you know, after seeing all this hardware, that without optical it is not possible, because this OGS station and all these things required very specific tracking. Then only this quantum key distribution happen. So we have to also work on this optical communication to make it happen. This quantum key distribution. So ISRO is basically working on this optical free space optical communication as well. And one other advantage apart from this quantum requirement, we have a very good bandwidth available, and there will be a very high data rate communication is possible with respect to this optical chain. So we have put 700 nanometer optical telescope at ground at our SAC OGS station, and we are going to demonstrate up to 1 Gbps of data rate transmission using optical mode from this TDS satellite. So for that, whatever the hardware is required, so these are the silent specifications which we are going to attempt, where we are roughly around 36,000 kilometers. Data rate is up to 1 Gbps, and around 1550 nanometer we are going to demonstrate, and our target is less than -9 BR, we can achieve it. So considering that part, we have developed onboard optical terminal. So all the hardwares are developed. These are the few photographs. So we can see that we have developed complete optical transmitter, data chain, everything which is required for the realization of this hardware. So this is our ultimate wish, where all the GEO, LEO, and this is the full-fledged operational scenario block diagram. You can see that there will be an optical chain, there will be a quantum key distribution happening in parallel, there will be RF chain also, and there will be a beacon for basically tracking and acquisition. So once everything will be at place, we will have a full, and ultimately at the end, this is not now, we'll have a secure 10 Gbps optical link with securing with the quantum key distribution. So that is the approved plan for that. And apart from that, as I mentioned, there is another aspect of this optical scenario is the high throughput satellite. So you know that currently the satellite community is facing a challenge to basically type of services at very high data rate. So in order to meet that, currently a lot of RF gateways are working in parallel, which can uplink the data, because single RF gateway doesn't have a capacity to link such a high data rate. So multiple RF gateways are there, and they are uplinking the data to make it happen. But once we having a mastery in this technology of optical, We'll replace all this RF gateway with the single RF optical gateway, and this will be supporting very high data rate. So in order to do that, we are developing all the technology which is required for, and currently our team is basically working on this domain to make it happen. Apart from that, the flexibility in the satellite is required RF channelization, like in RF. So similarly for optical also we require for RF channelization. So optical routing and switching, multiple channelization, variable bandwidth requirement. So all these things require flexible microwave photonics payload. So we are working on this direction as well to meet this requirement. Now coming to the what we are going to demonstrate with this TDS-01. Now this is about the technology, but I will now show you some real cases and what we are currently planning is with the upcoming satellite. So this is the picture, basically block diagram which I draw last night. You can see that these are the things up top side. You can see that this is basically will be the part of the satellite. So there will be a GNSS receiver sitting on board. There will be a optical quantum transmitter on board and quantum receiver. Earlier, once I team started developing this, we put Bob and Alice name, transmitter Bob and receiver Alice. Then my director fired us, why don't you put some Indian scientist name? Why you are going with the Bob and Alice? So we renamed the onboard data transmitter and receiver and put it Aryabhatta and Bhaskara. So Aryabhatta is basically onboard QCU where we'll generate onboard quantum key, and QCU for ground key generation will use this Bhaskara. And actually what happens, this photon on board will be basically 4 diodes are there, and they will be randomly switched based on the random key distribution. And the first operation, what will happen, this optical beacon first gets synchronized with the optical receiver at the ground. So for that, optical ground station will get synchronized with the satellites. Once this optical synchronization beacon synchronization with satellite happens, then this random photon distribution will happen from free space, and our optical detector will detect these photons at the ground. So typically what we have estimated that in this BBM84, we can hardly receive only 1 or 2 photons at our receiver end. And once we receive these photons, we'll basically time tag these photons. And through Bhaskara, again, we'll resend these time tag photons to onboard through RF chain. And once the RF chain onboard receive this time tag photon, it generates the key based on the time tagging. And similarly, the received photon time tag will generate a key for ground. And once we transmit the encrypted key with the onboard generated key, if my synchronization is perfect and whatever the time tag photon is correct, the key which is generated at ground using in Bhaskara will try to decode the onboard encrypted image. And if the protocol is working well, we are able to securely decrypt the image. So this is the basically the whole concept of space to ground QTIS system. And we'll receive after everything it gets synchronized and key distribution is correct, we'll receive decrypted image at the ground. And coming to that part, we basically started working on this, and this is the you can see the realized payload which we realize in Space Application Center, and we have flagged out of this payload from SAC in November 2023, and our director SAC has flagged off this satellite from SAC Space Application Center, and it has been airlift from Ahmedabad because this is a very critical in fragile hardware. So we airlift from spacecraft whole payload to Bangalore, and now it has been integrated with the spacecraft. There also, after reaching the space, integrated with the spacecraft, we did the thorough testing. So in order to do this thorough testing, we taken all our ground hardware again airlift from Ahmedabad to Bangalore, and we tested this protocol. So I will show you some photographs of our testing there in Bangalore. So this is the, you can see this is our TDS spacecraft, and this is our complete ground hardware which we have airlift through spacecraft. And there you can see this is the ground OHA, and this is the onboard OHA where we did this line of sight and verify our QKD protocol testing. So based on that, we did actually what happens once we receive the payload at Bangalore, we call a disassemble mode testing. Before integrating with the spacecraft, we try to test the payload as it is so that any this malfunctioning happened due to the transportation. So we call as a disassemble mode testing. So where we have tested all these things as in the disassemble mode, and then we integrated this complete payload with the spacecraft. That is called as assemble mode testing. So same test again we verified in the presence of the spacecraft. So the power and bus now is connected with the spacecraft. Earlier it is independent. So all this testing like PAT mechanism verification, optical downlink, OHA corrections, all these things we have tested both in disassemble mode and assemble mode. Apart from that, as I mentioned, the most critical technology which is will be the part of this quantum satellite is the PAT mechanism. So there is a specification laid down for there. So we verified all the specifications once the spacecraft reached there. So we verified. So this is the specification, and against this specification, we achieved this much at the spacecraft level. So you may ask, sir, actually satellite has to work from 36,000 kilometers. But right now you are testing this spacecraft in lab environment with line of sight. So how these two scenarios are equivalent? So what we have done it, we estimated the type of losses which we are going to basically face once the spacecraft reach at 36,000 kilometers. And accordingly, we simulate how much power we'll receive at our OGS station at Ahmedabad. So what we put it from the satellite, once we started this transmission, we put some optical attenuators so that the exact scenario at the receiver end, we can able to simulate it. So this result, not the exact line of sight, we put lot of optical attenuators between satellite or our ground test system so that we can basically simulate the exact ground scenario. So that way, basically, we would not only just line of sight test, we basically trying to test the satellite with the exact scenario. And similarly, the type of moving platform. So we put a moving platform below the satellite and we simulate the actual scenario, what satellite is going to face in actual operation scenario. And that scenario, we test our PAT mechanism, whether it is meeting as per requirement or not. So on that scenario only we have tested. So this is a very interesting photograph. So what happens in actual scenario once this our OGS station will once the satellite will be on the space, it will try to scan the basically try to detect this optical beacon which is coming from satellite to ground. So initially it will scan all the background which is behind the satellite, and if my this PAT algorithm will work beautifully, then what happens? You can see there is a dot coming at the center. So this is basically optical beacon. So in actual scenario, also this type of dot will come once our OGS station able to track the satellite. So if our tracking is perfect using onboard PAT and ground PAT, then what happens? We'll receive an exact dot. So this is the result, not a simulated result. This is the actual test what we have done it at our satellite level testing at Bangalore. So this is the dot will come. So we'll detect. That means we are able to detect the optical beacon. Now the satellite is locked with our OGS station. So once this is OGS station is locked, we'll get lot of basically pointing points. So basically this locking, what I am showing you, is basically is in two parts. One is called coarse acquisition, and another is called fine acquisition. So these are the basically coarse acquisition parameters which is required for our satellite to track. And after the coarse acquisition, then the fine acquisition will work. So this will be done in autonomous mode. Nothing manual intervention required. We have put such an algorithm that once it is the coarse pointing acquisition will be done, satellite will automatically, and even our OGS ground station will automatically track, go in fine pointing mode, and it will try to track the satellite. Apart from that, as I mentioned, that there will be an optical chain as well on board. So after this tracking, we'll going to not only doing to demonstrate quantum chain, we're going to demonstrate our optical chain as well. So there we'll try to demonstrate these two data rates, and we did this testing in satellite level also, and we receive all this mode we have verified. And we basically put SSR on board a solid state recorder where we have pre-stored this image, and through satellites once we transmit this image. So this is the actual receive image which we received while testing at satellite level. So we have put Indian flags on board. So that flag data we received through our optical link at the ground. So this is the basically actual testing while we're doing the satellite level testing. Apart from that, as I mentioned, this quantum chain also is verified at satellite level. So in quantum chain, actually, this our quantum pulse frequency are in three modes: 12.5 megahertz, 25 megahertz, and 50 megahertz. So we have checked in all three modes. Then we have a secure key distribution at around 10 kbps. So we have verified that a geo scenario. Then we check our Q bar, because Q bar if greater than 10%, then it's very difficult to generate a key both onboard and ground. So we are able to achieve around 3 to 4% Q bar. And then we have verified this our RF chain link also, because this is anyhow required to basically back support. So this basically working at 4 Mbps. So this we have verified. Then this our key of QKD demonstration. So we have basically gone for two modes. One is the larger mode, which is called a OTP of image. Means based on the image size, the key will be generated. And another is that a fixed mode like AES-128 protocol, where the one fixed 128B key will be generated. So in the both the modes we have put on board, and both the mode we have verified at satellite level. And then this pulse repetition frequency, we have verified it. So this is the basically our GUI. You can see that this is the basically actual GUI. Even in the real satellite test also, will you going to use this? So you can see that there is Aryabhatta on board, and there is a Bhaskara at ground. So Aryabhatta is the one where we're transmitting. Once we are able to receive, we'll got this light that we are able to receive this thing. And you can see there is a Q bar display. So basically this Q bar will be only come when the key matching will happen on board and ground. And once this key matching will happen less than 10%, then only Bhaskara will able to generate a key, and it then will going to test the actual thing. So as I mentioned, there are various modes. So in every mode, we have already pre-stored few images, but there is a possibility that from real time also we'll capture some images and secure through our onboard key distribution things and demonstrate at ground. But suppose something happens, we have already put some pre-stored images at SSR on the satellite. So these are the few results where we did the encryption using OTP mode. We can see that this is the encrypted image coming at our Bhaskara. And once we generate our onboard key, ground key, and try to decrypt, it get decrypted because our protocol is working fine. Similarly, for AES mode also, we gone for 128-bit type of encryption. So there also we did the encryption using AES 124 and then capture at ground, and we are able to successfully recover the image. So basically, this demonstration shows that our QKD protocol is working actively, and whatever the assumptions what we made it for onboard and ground is working perfectly okay. So these are the few QKD protocol, and then as I mentioned, this backlink is required, RF link also. So once we connected with the satellite, we tested with the complete Ku band link. Actually, this RF link is in Ku band. So our optical, this apart from quantum and optical transmission, there will be RF transmission as well. So RF downlink and RF uplink will happen in Ku band. So this test, whatever the result which I am showing now, is with complete RF change. So the full satellite mode we have tested at Bangalore, where everything is as per the requirement. Now coming to all this quantum and optical, what are the things which is required for our future technology and what are the current trends? So as you know that currently we are in 5G environment, and very soon we are going to migrate from 5G to 6G. So as you see this basically increase in migration from 1G to 2G, 3G, 4G, there is a huge change in data rate. But now what happens in 6G, everything will go integrated together. So again, there is a huge jump in data rate requirement. So if you see in current scenario, like our DTH satellite transmission happening, like DDH, digital video broadcasting, satellite through internet, every services is now going to integrate together and make it happen using in 6G. So, but now what satellite community is going to face is basically the cost, because you see that due to the fiber optical links, we need to compete with the terrestrial technology, that our whatever the services you are getting from fiber optical links at the same cost can be provided through satellite. So if you are able to provide, then only your technology exists. Otherwise, no existence will be there. So another thing is nowadays another terminology comes like cost per bit. How much cost is required to transmit one bit from here to the terrestrial to another place? So this is also a very basically niche challenge what we are facing, that we need to reduce the cost of the through the data transmission, and in the same time secure also. So these are the current challenges. And another thing is that the type of services what we are offering, type of data rate what we are offering, that also needs to be increased drastically, if at all we are having in the market. So these basically required for a lot of flexible coverage, lot of flexible requirement in terms of payload, lot of secure link are required from satellite, lot of like I mentioned that feeder link, apart from RF, we required optical feeder link, lot of quantum chain is required having a security on board. So these are required a very flexible architecture of the payload, very high throughput requirement of the payload, and the payload architecture is such that based on the user requirement, we can reconfigure the satellite. So these all lead to basically call for a high throughput satellite, and we are working on this satellite. Basically, this is high throughput satellite. So if you just compare early days when we have a Doordarshan in 80s, there is a global over India beam. One beam is there where there is a transmission from Doordarshan, and it is through Yagi antenna we see the Doordarshan program. But if you see now, this global beam is vanished. Now there is a very small beams are there, and these beams are basically, if you see the color, means these color, like this orange color, basically these are the same frequency bands, but they are getting reused. And this different circle means different type of services satellite is now providing for the different user. So nowadays the scenario is like that, that single satellite will divide it into multiple beams, and each beam had basically based on the user driven, and each user has a different type of service requirement. And suppose some user require 2 rings, then satellite is able to configurability to convert the single small ring to the 2 larger rings. So this type of flexibility now required, and that is called for a high throughput satellite. Apart from that, as I mentioned, that this spot beam, the feeder link is, and the feeder link should be now required very much in optical domain, having a secure quantum link. So if at all we are going for this high throughput type of satellite based on the flexible configuration, we need to adopt this quantum technology. We need to adopt this quantum technology and optical technology to work as a feeder link for this multiple spot beam type of technology. So apart from quantum and optical, in satellite technology, these are the one slide I just put it. We need to work on the propulsor system of the satellite, because satellite life need to be increased. Structure, because bigger and bigger satellite is going to make, so structural capability needs to increase. The solar panel capability needs to be increased. Satellite control electronics, because optical OGS from optical to satellite to ground with optical connection required a very micro radian type of accuracy required for the pointing. So satellite platform stability, satellite control handling required to be improved. Satellite pointing accuracy need to be improved. Antenna side, we have to put lot of spot beam type of antenna design, which the least interference will be there. Satellite, since that type, so many beams are getting configured, so satellite having a very high power type of thing. So satellite thermal handling capacity needs to be increased. So these are the niche area where academia can work as a part of future R&D and provide the solutions to ISRO to basically to improve and more work towards the high throughput satellite. So if you ask me what is the future of our drives, so we have to improve our overall throughput. We have to go more secure. So in terms of overall high throughput, although one part is that we go migrate on optical technology, another part that we can improve our modulation efficiency. We need to migrate more higher bands like optical or more further higher side. We need to reduce our cost per bit to basically then only user will use. Otherwise, everything is, as you know, in the world is cost driven. So if our cost is very high, nobody is going to opt our satellite technology or quantum technology. Gateway efficiency need to be improved. Flexible architecture need to be worked out so that it can change, because what happens when the satellite is launched, if you are no flexibility on board, the satellite will be no use after some years. So satellite architecture can be flexible so that based on the market demand, we can reconfigure the satellite, and the processing of the payload has to be increased. So this basically call for overall change. So I think that's it from my side. I hope I try to cover what ISRO is lagging behind and where we are right now. But my request to academia is that lot of niche technologies are there where you can work on. So earlier, what happens in ISRO, once we are doing the research, we invited ideas from academia who can contribute from ISRO R&D. But that time, the problem what we faced, that academia did not know what ISRO is required for. But in order to solve this issue, every year we are releasing a basket called Respond Basket. So this year basket is also released. I think every year we are releasing it. So this year basket is called Respond 2025. It is fully PDF document. It is available on ISRO website. And the earlier date is to 31st December, January, but now it has been extended to 15th February. So there, if you can see that our SAC and other centers also release some niche technology where we invited academia to collaborate with us for the technology. There you can see that for the quantum also, and for the advanced signal processing also, for the other real problems what we are going to right now we are facing, we invited the application from academia. So please participate and do contribute for the NESR building. So that's all from my side. And now I am ready to take the questions from the participants.
Thank you so much, sir, for a really wonderful presentation, sir. Actually, when is I'm audible to everyone?
Yeah, madam, you are audible.
So thank you so much for this wonderful presentation. Actually, I'm surprised a little bit that we are doing so much in quantum, especially in ISRO, and we have a full architecture, and we are actually, we are actually doing these things. Because in academia, we mostly don't get insight that what is happening in ISRO. We know that okay, PSLV is launched, we know this satellite is launched, Gaganyaan is going on, but we don't know what is scientists doing inside, right, sir? Normally.
Actually, madam, we are the silent worker. We are just working
Yeah,
for
yeah,
the
yeah. But you are
country.
that should be, I think, appreciated. I don't know, sir. You are online. Otherwise, it's a huge. I just want to praise in like maximum possible way that what you people are doing. Hats off to you, sir, first of all, from a
And
bottom of
madam,
my heart, because
yeah, madam,
it's a
and
great thing.
yeah, madam, and if you are this success in this TDS satellite, we are in the world second apart from China who has done this real-time quantum key distribution from the satellite. Even USA
Yes.
did not succeed till now, madam.
Yes, sir. So hats off to ISRO, and hats off to all the scientists working towards this. Sir, you are a silent warrior, I will say, because in academia, people mostly talk, okay, that Indian R&D is not that good. Because I am also a researcher, so I know what people talk. That okay, R&D is not that so good. We are lacking from foreign. We are lacking from. We normally talk this, but really, we should really appreciate that what kind of scientists working in our India, and we are where we are approaching. So
Madam, just
before any question, I want to appreciate to bottom
yeah,
of
yeah.
my heart, sir.
Apart
uh,
from madam, since there is a time available, I'll just like to share one another story where we are
yes sir,
now
please.
right now the frontiers. So you know that our own navigation program, because I am heading this division, so nobody will tell better than me.
Yes.
So basically, what happens during '99 Kargil war, once this Pakistani troops captures our peaks in Kargil region. So what happens? We need to basically uh, t- we need to go to remove the soldier. So we are dependent on that time. GPS is providing services to Indian Army and across that region. But that time, US, what they have done, they have switched off the services in this region to make it basically. I am not favoring India, not favoring Pakistan, but in fact, indirectly they are favoring to Pakistan, because once these services have been switched off, our soldiers have manually go to top of the hill to infiltrate to remove the soldier, and because of that, lot of soldiers are died due to the not getting proper path or not getting proper direction. So at that time, Indian government realizes that should not depend upon the foreign GPS and Galileo or any other foreign navigation player. So that time we have decided to go with this NAVIC program. So NAVIC program started in 2010-12 time frame, and but that time we don't have much readiness in terms of technology. So the niche technology which is required for this NAVIC program is the basically atomic clock. So at that time, globally, there are two atomic clock players which are basically uh, there to supply this atomic clock. One is the company called Spectra Time from Switzerland. Another is company from US. So that time, US company didn't having export licenses, so they denied it. And we are only one vendor left with is called Spectra Time. So we have procured this atomic clock that time from Spectra Time, and we started making our NAVIC satellite based on our signal structure. And that time, what happened, madam? Once we applied for this direct satellite, US intentionally did not give us L1 band signal, L1 band frequency band. This is the most common band used by GPS, Galileo, all navigation player. And even in your mobile, whatever the GPS signal we are getting, it is from mostly from L1 band. And we didn't get the license of L1 band because due to the monopoly of GPS, and we got a permission from L5 and S band. So with that time decided anyhow, whatever the band we got it, let us start the service first. So we basically made 7 satellite using L5 and S band, and the first generation of Navik is completed. But what happens, madam, this atomic clock, which is very costly. Right now, if you are going to procure this atomic clock, this cost will be around 10 CR for the single piece. So what happens, madam, during this clocks is also new for Spectra time also. So this clocks is getting failed on board, and even not in our satellite, Even this Spectra Time supply this clock to European navigation player also. So their program name is called Galileo. So there also this clocks is getting failed, and in our program also it is getting failed. So our 4th satellite has gone bad because of the failure of these clocks. So during 18-19 time frame, when our director Nilesh sir was there, we realizes that it's a totally dependency on technology. If you depend upon foreign players, so this type of glitch is bound to come. And that time we precised two things. One is this atomic clock development. So we have opened a new lab and started development of this atomic clock in house. And then we are again forcing the through our current government to having a licensing of L1 band signal. So by pressurizing our government politically, we got a permission to transmit this L1 band signal. But in L1 band, what happens, madam? This is the most crowded band, and there is a restriction of signal structure. You cannot design any signal and start playing. So we have to there is a fixed frame length, there is a fixed modulation. So everything need to be fixed. Then only we can launch. So, but what happens? We are at the last because that time every player in the world like China, Galileo, Russia, and USA, everybody having their own L1 band signal, and each one has then their own patent. So we asked US that time, since we got the permission of L1 band, why don't you allow us to fly your old signal structure, means your own modulation, coding, and all? We can use as it is. Why we are doing that? Because we want that whatever the chip manufacturer, whether it's a mobile chip manufacturer or any other, we'll use because they will not going to make ASIC for us. So our software just fit in inside, and we can directly come into the market. But that time, once we talk to GPS guy, they give us the license only for 5 years. So that time, after GPS discussion, we did the internal discussion, and we saw that suppose we got a license only for 5 years. Later on, with our relation with US is not good, they may ask to stop this signal. So, and that is the right now, if you see the current scenario, that is happening because our relation in US is not very good. So that time we have taken a call that will not depend upon GPS or any signal structure. We'll take 1 year time, and we divide it into teams, and let us start developing our own signal structure in terms of modulation and coding. And I lead the team who developed the whole coding scheme for this NAVIC, and we develop ingeniously all the codes, frame structure, modulation required for this NAVIC program. And we develop in-house everything. And I am happy to say that whatever the code in structure we have designed, it is better than GPS, and it is completely ingenious developed. We got the 4 or 5 patents on this signal structure, and all my patents are basically for that only. And we publish as a part of our ICD because this any receiver manufacturer across the globe who wanted to basically receive this L1 band signal of NAVIC, they can develop a receiver based on our ICD. So this ICD is available on ISRO website, freely downloadable. So all the design in-house, and we presented our signal structure to GPS team, and they also appreciated that your design is much better than GPS. So that way we did the complete Make in India transform. And then we talked to our all mobile manufacturer, like whatever the biggest there. And now the NAVIC signal structure is part and parcel of even iPhone 17. It is started from 16 time frame, and now it is in 17 for all major mobile manufacturers. And we design such a way that nobody need to redesign their ASIC. It's just a software upgrade because we've taken care of signal structure such that it is exactly fitting in GPS, Galileo, or any navigation player, but the performance is better. So that story I wanted to share with that within the 1 year time frame, we develop our own signal structure, our own payload, and from NVS02 onwards, this signal structure is going on. So L1 band signal is now transmitted from NAVIC satellite. And this atomic clock also we developed in-house. It is then successfully tested. And from NVS02, means second generation of NAVIC satellite, NVS01 onward, our indigenous atomic clock is flying. And since last 4 years is working very well. And this is our now prime clock for all our future satellite, madam. So we are now saving all around 10 CR for each clock. And now we are ready for inviting in the Indian industry to make this clock in production mode so that we can export this clock globally also.
Thank you so much, sir, for updating about this information. Because from news, we know that during the Kargil war, US didn't help us. That we know. But in a technical term, where it didn't help us, then we came to know today from you, sir.
Yeah, madam.
Thank you so much, sir.
Thank you, madam. And after this NAVIC operational, government is laid down this navigation policy. So after whatever the vehicle is going to sold in India is having a NAVIC chip in-house. So this toll-free, toll detection, everything is based on NAVIC now in future, madam.
That's great, sir. That's great, sir. Thank you so much, sir, for doing this for our country, for ourselves, sir, and for updating us. Because as a we are sitting remote here, and what is happening during the war, what is happening in our technology development, generally we don't know about. Thank you so much, sir. Now I will take questions from participants. Please, participant, you can ask any question.
Okay, so good evening, ma'am. This is Siddharth Sharma from Dr. B.R. Ambedkar University, Agra.
Siddharth, yes.
Go ahead, Siddharth.
My question to yes. My question to sir is, sir, your talk was very clear and insightful. Thank you for that special talk. My question to you is, QKD communication, isn't it more prone to atmospheric disturbances than classical communication? So what can we do to, solve this problem as well?
It's a good question, Siddharth. As I mentioned during our initial presentation, the talk itself, that atmospheric modeling is very much required for this line of sight communication. So our application team had done the atmospheric modeling and estimated the type of losses there. But that is based on our theoretical assumptions. So until unless we do some practical communication, then only we can validate this model. Although, as I mentioned, during drone and flights, some testing we did the practically. But you can participate in this theoretical modeling also to make it more robust, so that once we do the real communication, it can be directly meet as per our specification.
So, sir, can we take these disturbances as resource rather than considering it in later stage in theoretical modeling? Can we consider these disturbances as resource? I mean, I guess.
And what type of resource are you talking?
Suppose in the course of communication, suppose we are trying to model, like you have said, we are trying to model this atmospheric disturbances. So rather than considering these disturbances as disturbance, we consider them as a resource while programming something else. I do not know. I mean, I'm asking for.
So currently our status is that like that because right now our wish is to basically successfully communication between satellite to ground. So whatever coming in the path which basically do the loss for us, we are right now accountable for that. But what I basically understand from your statement that we want to utilize these losses for some other applications. So if you have any idea regarding what type of application you are targeting, you can write me a mail. I can very well guide you because right now our focus is basically to be having a successful communication between satellite and ground. So this we are considering as a loss only. But if you have any other idea where it can be used for some other application utility, you can very well discuss and drop me a mail. Accordingly, I can guide you. That's what I can say right now. But I'll appreciate that you started thinking something different. This is what we required for academia across the India, that we can start thinking differently. Then only we can come out with some novel thing.
Okay, thank you, sir.
Thank you so much, Suraj. Next question. Sir, I have one question. Meanwhile, I will ask.
Yeah, Divya, go ahead.
Yeah, sir, I want to know about that single photon source, right? It is in-house.
Let me tell you, Divya, the actual story, what happens. So what happens in satellite, will basically from geo orbit, roughly, let us say we send around 50,000 photons to ground. But what type of losses, what we are estimating either from space or from free space everywhere, what is our hinge is that only 1 or 2 photon we are able to detect meaningful photon at the our optical head assembly. So basically once we receiver it. So this photon is not a fixed photon, it's a random photon which are released from 4 different diodes based on our random number generation. Okay. So the photon which we receive at the receiver end will time tag that. This time, this is the photon in this phase we have detected it. So this is unique because each photon which is coming from the onboard is unique in their phases and their time tagging. So once we detect that, so that information we need to, and that information we received it at our ground receiver only. Na? So same information through RF chain will send back to onboard. This is the photon which we have received at ground at that time tag. So then the onboard transmitter will know that this is the photon which we have sent that time tag. The receiver is having that information. So onboard, whatever the photon which we have transmitted with that time tag, they will encrypt the one bit with that key. They will generate the key, and the same photon which we receive at the ground with that will generate the same key. So if both photon same phase or same thing is there, the key will generation onboard and ground will be same. So that is the whole idea. Basically, it's a QKD protocol only, encryption protocol only, but now it is happening at photon level, not at the RF level. That is the only difference.
Yes. Okay. Thank you so much, sir. I know it's like for a physics people, maybe core physics people, it's a communication, right? It is it's a optical communication. Yeah, it's coming. So any more question, participant?
Actually, Divya, if you talk about this atomic clock or this quantum, everything is physics only. So we are doing a lot of physics, but we are the implementer one. We learn physics that much. This is required to develop a system, not in such a deep like a things, but we do physics, but based on our product requirement, not beyond that.
Yes. And sir, we have an optical clock, atomic clock in NPL, if I remember right.
No, Divya, that's the difference. The NPL clock is the ground clock, and you can get a lot of ground clock, like passive hydrogen measure-based clock. So NPL is not only having a rubidium clock, they have a cesium clock, they have a hydrogen measure clock. But these clocks are ground clocks, and you can get thousands of vendors to having these clocks. But having an atomic clock on board, it's a niche technology, very niche technology. And as I mentioned, the one onboard atomic clock cost is around 10 CR to purchase a one atomic clock on board. So there basically it's a basically space environment. It has to work very precisely, and all this navigation timing which we are talking now, GPS timing. Basically the fundamental clock is the atomic clock, which governs the whole timing and position. So each GPS satellite or each NAVIC satellite having 3 such atomic clock on board. One in cold redundant mode, another one is hot redundant. Suppose any clock gone bad, we need to replace this clock. So NAVIC satellite currently having this 4 clocks. So right now we are now migrating towards procure clock to indigenously developed clock. So our current satellite is now working on our indigenous developed atomic clock. So this is the very niche technology which I am talking about.
Yes. I'm just thinking about the level of precision we have.
Yeah. So you can assume that the clock stability, what I'm talking about is long-term stability of order of -14.
That's why I'm just thinking the level of accuracy, precision we have.
Yeah.
Even as a researcher, it surprised me again.
And you came to surprise that all railway timing is now synchronized with NAVIC satellite. Yes. In fact, if you come to SAC, we have a very big clock display in our campus gate. This is called a NAVIC timing. So you can basically synchronize your own hand clock with the NAVIC clock.
So now I am really excited to visit SAC. Really.
Yeah. Please come.
Thank you. Thank you so much, sir. First of all, I want to introduce. Sir is my senior. Sir is PhD from the same department. I am PhD from the same department. I heard his name, but I never met him. This is first time I am meeting him. I know some senior work in ISRO. I never know as a face-to-face. We never talk. So thank you so much for this keynote talk and for discussing insight about how you work in ISRO and how all the things. Thank you so much, sir. And we will continue our discussion beyond this talk also, sir, beyond this keynote talk and our course also.
Yeah, and whomsoever participate, any help is required regarding the research in ISRO, please feel free to contact. I am slightly busy because we are working in the payload area, but whenever I have a time, I will definitely going to reply.
Thank you so much. Please participant. If you're interested to work on the problem, you already know it. You can drop a mail to sir or you can contact me. Okay, no issue. So Divyanshu, please present the certificate of appreciation to sir. So this is a very small, a heartful recognition for your valuable contribution as a keynote speaker for this short-term course on quantum technology for innovation and startup. We deeply appreciate that your dedication, your sharing the profound knowledge, expertise, and insight on the topic future of quantum satellite communication and Indian scenario. Thank you so much, sir. Your time, effort, and your discourse greatly enriched the learning experience for all the participants. Thank you so much, sir. Thank you so much, sir.
Thank you, madam. And anytime for HBTU, I'm ready to support any aspect. Please feel free to contact because it's my state and it's my responsibility to basically add on the development, whatever is required for. So again, thank you, Divya, for inviting me. Now, Divya, I have to leave.
If you are visiting like your Varanasi state, please let me know. We want to invite you to HBTU as a person also, sir.
Yeah. Actually, I was now part of advisory board of IIT BHU. So last month I was there for departmental review of electronics, electrical and physics. I visited the IIT BHU physics department also. But next time, whenever I will be in IIT BHU, I will definitely like to come HBTU also.
Yes, sir. Please. Okay, sir. Okay, sir. Thank you, sir.
Madam.
Thank you so much.
Thank you.
Okay. Thank you so much.
Madam, and now I'm leaving. Thank you.
Okay. Thank you, sir. Okay. Dear participant, we are very soon going to have our second talk. So we are giving just, I think, 5-minute recess. Okay. I think our guest already joined the talk. Dr. Aswath Babu.
Hello, Divya. Yes, hello, Divyaji.
Hello, sir. Hello. How are you, sir?
I'm fine. How are you?
I'm good, sir. We are giving our participant, I think, 5-minute recess to start your talk. We will start from 3:30, sir.
Yes, please.
Okay. Thank you, sir. Participant, please mute yourself because very soon we are going to start our second talk of the day one. Again, a very good afternoon, everyone. We are going to start our second session of day one, and our resource person is Dr. H. Aswath Babu. First, I will briefly introduce our speaker, Dr. H. Sir, are you audible?
Yes, ma'am. Yes, I can hear you. I hope you can hear me.
Yes, yes. Thank you, sir.
Oh, great.
Dr. H. Aswath Babu is an physicist and quantum computing researcher currently serving as an assistant professor and head of the Department of Art, Science and Design at IIIT Dharaawd, Karnataka. With over a decade of academic and research experience across India and Europe, Dr. Aswath is specialized in quantum machine learning, quantum neural language processing, quantum internet simulation, and quantum sensing with NV centers. His multidisciplinary experience with quantum physics, AI-driven application, and large-scale quantum network modeling. He has undertaken impactful postdoctoral research at IIT Madras and Lund University, Sweden, focusing on quantum electrodynamics, nonlinear optics, and advanced optical phenomena. His current research includes developing scalable quantum secured internet architecture, hybrid quantum classical learning frameworks, and QNLP pipelines tailored for Indian languages. He is the principal investigator of multiple funded national and international research collaboration, including partnership with Nevada and the University of Bonn. Dr. Aswath has delivered numerous expert lectures in national level FDPs supported by AICT, METI, DST, NQM, and QGC, covering quantum computing, quantum sensing, quantum AI, and statistical physics for quantum technology. He has also been recognized among the top 30 resource persons under the Atal FDP scheme. His teaching portfolio spans fundamentals to advanced quantum courses, and he has played a central role in establishing the minor program in quantum information science and technology at IIIT Dharaawd. With a strong publication record, including contribution to Physical Review A and several cutting-edge quantum AI papers, Dr. Aswath is widely regarded as an influencer, educator, and researcher shaping India's emerging quantum technology ecosystem. Thank you so much, sir, for accepting our invitation for this program. We are really blessed to have you because I heard you on my quantum computing journey. I heard your first lecture. Then I decided to welcome you in this event. Thank you so much, sir.
Thank you so much, Divyaji. It's an honor for me and very pleasing to be one of the resource person for this wonderful the workshop. Yeah. We can start the session. So I am using my tab to share the screen. Let me try to share the screen. Divyaji, can you just exit sharing the screen?
Yes, yes, sir. I think screen is not coming yet.
Yeah. I think you may need to give the privilege for just a minute. Share the content. I'm trying to log in through my tab. Let me give again. Let me try. Okay. Just a minute.
No issue, sir. No issue. You can do it.
It is trying to log in from my browser. Okay.
Yeah, it will come. It will come. Yes, I think some request is coming.
Yeah, I'm trying to share the screen there. Okay. Share the content. I just want to use my. Just a minute. Is there any way you know how to open?
Sir, there is one option, share your screen, something like that. In Team, there is a share your screen.
Yeah, that I know. That I know. The thing is, I want to use my webinar Wednesday. How to open in the? Okay, just a minute. Did you add meeting link, meeting options? Just a minute.
No issues.
Can you send me the link?
WhatsApp, sir. Again, WhatsApp.
Can you WhatsApp me?
Yes, sure. Just a
WhatsApp, I'll try.
Yes. Just a minute.
I can share the screen with laptop. That's not an issue. But I want to use my handwriting in between.
Okay, no issue. Just I'm sharing. Yes. Just I shared on your WhatsApp, sir.
It takes some time. Again, it is opening through browser on the tab. I am little bit hesitant.
Yes.
Okay, let me try to share the screen. Share the content. Oh, it is not allowing the content share.
Maybe the tab problem, sir. Maybe. Otherwise.
Share. 1 minute. Send device use supported. Quick share. No. See, share the screen, right? Share the screen.
Yes, sir.
That's the option. This is a share the screen. It should ask me.
You can share window also, and you can.
Okay. Microsoft Teams, how to open a particular meeting? Any idea? New meeting? Add account, invite, notifications.
Devanshu, can you help? You can listen to sir if so.
New meeting. Contact. Community event, meet now. Share a meeting, invite, copy. Meeting options.
Sir is not able to. Okay. So maybe you have to install the MS Team to share from tab.
It is there in my tab.
Okay.
It is there.
Okay.
It is there. Let me close everything. Microsoft Teams, right? Yeah, it is there. Now, only thing is I have to start join with the meeting ID. Okay. What is the meeting ID?
Okay, just a minute. I'm giving you some meeting ID.
Meeting ID.
Yes, meeting ID is I'm sharing with you, sir. Just a minute. Okay.
And also meeting passcode also?
Yes, yes, everything is there. You can see.
If I get that.
Am I audible? Am I audible?
Yes, yes. Yes, yes, yes.
So the meeting ID is 938.
1 minute. I'm just copying. Okay, meeting passcode is also there. Okay, 1 minute. Every time it is trying to open through browser, so that I don't want. Capital H A9 EW. Okay. Join now. Yeah. So you might have got the. Yes, I am able to join. Let me share the screen now. Yeah, I think it is share the screen. Entire screen. Start.
Yeah, it is coming.
Has it come?
Yes, not slide, but I think you are sharing the whole
Yeah,
screen.
that is fine. I am there, right there. So that much is enough for me. Yes. So yeah. Yes. Okay. I think you can see, everybody can see my screen.
Yes, yes, yes.
Yeah. Thank you. Thank you. Okay. We wasted like 5 to 7
That's
minutes.
fine, sir.
I'm sorry, the participants, kindly excuse me. Right. So once again, thank you very much, Divyaji, for such a kind invitation and also brief introduction of me. So it's a very pleasing opportunity for me to share some of the understanding which I gathered for the past decade or so on quantum computing. So you had a wonderful session at 2 to 3:30 from a resource person from ISRO. Amazing application. You might have got the ideas with quantum computing. So as we need some basic understanding, I hope some of you people already have some background. So kindly bear with me. I would be starting from the scratch, simple things, and from there I try to build. Okay. I have say something around 1 hour 15 minutes from now. I'll try to concise things and make it more elaborative at the same time. Okay, so this is a talk on the fundamentals and the understanding of fundamentals, how we can lead to applications, right? And some research opportunities also, along with one of the research opportunity which was shared earlier. Along with that, few more I will be mentioning at the end. Okay. And also at the same time, let's make it more interactive. So Divyaji, I want to know whether the participants are allowed to unmute and speak, or they will be sending their questions in the chat. How it is working?
So normally we don't allow to unmute because there is a lot of disturbance. So in the last, we will participant will collect their questions and they can WhatsApp me on the group. If sometimes what happened, the chat box is not working. Otherwise, they can put in a chat box or in a WhatsApp group. No issue. In the last, we will discuss.
Yes. So meanwhile, if something, if people are not at all understanding something I said, so please don't hesitate to put up in the chat. I hope it should work throughout. If it doesn't work, as Divyaji was mentioned, at the end we will take the questions. Okay, great. Right. So some of you might have seen me giving some talks here and there. I usually prefer blackboard writing more than presenting stuff. In that way, it is more easier for me to convey what I need through writing and drawing some figures and writing some equations. That is the same thing I would follow now as well. Okay. So let me go further to the next slide. Okay. And again, a lot of text also will be put up in my slides just to convey the idea which I had intended. Later on also you can read through and understand. Okay. So don't worry about this text. I will explain what it is. Okay. So the first slide, what I want to convey here is right now we have quantum classical computers with us. Okay. So the classical computers are there anyway. The question is, why do we need to go to quantum computers? Okay. So why do we need to go to quantum computers? That's a question we should ask ourselves. There is somebody, Suraj, can you mute?
Sir, just any person which is unmuted, please mute. Otherwise, I will remove everyone from the meeting which is unmuted, because I am really focused on listening this talk.
Yes.
Okay, please.
Ma'am, as an organizer, you can mute, I think. You can
Yes, that's fine. Yes, yes.
Okay, great. Okay, sorry. Right. So the question, very simple question we should ask ourselves. Every time a new technology comes up, or new idea comes up, they are there to ease up our day-to-day living, okay, day-to-day work. In a similar fashion, we are happy with the existing computers, right? And the question is why we should go for quantum computers or a quantum computing in the first place. That's a question we should ask ourselves. Right. So in a similar fashion, back then in 1960s to 70 and 80s onwards, that is the time, right? People were trying to understand some of the physical phenomena around them. One such a phenomena is a biological process. For example, if you just take a process something called photosynthesis, okay? So if you take a photosynthesis, what happens? It happens with a very good accuracy, right? What I mean accuracy means is if you just take how much sunlight plants take from the sun rays, and the minerals from the ground, they were able to achieve a very good efficiency in the conversion rate of sunlight to the required energy nourishment for the plants. Okay. So this happens with amazing efficiency. At the same time, we humans were unable to replicate the same conversion efficiency. For example, I think you can just mute them.
Continue. Right. I will keep muting. Don't worry, sir.
Okay. Right. So just a minute. Yeah. Okay, so can you see my screen? Yeah. So what happens? The efficiency we want to achieve. That efficiency people were trying in 1960s and they were not able to achieve. One simple thing they can do that time is try to understand how this process is happening. Okay, so how this process is happening, they were trying to understand. And there's a lot of parameters are involved in understanding this process. Parameters in the sense, the dictating variables involved in the process. Okay, so lot of parameters, lot of data needs to be put on, and lot of analysis has to be done. And the existing computers, whatever classical computers were there that time, were not able to take the load from the context of information storage, from the context of processing. Because of that, people are not able to load the entire information to process. Or for example, if I want to solve something, I set up some set of differential equations or some algebraic equations. At a time, I have to solve them to find the answer for my requirement. But when it comes to photosynthesis, people were struggling to do so because very simple thing is the computers are limited space memory wise. At the same time, processing wise also very much limited. Right? So that time they thought, what can be done? So that is the time this person came along, Richard Feynman, a famous physicist. Okay. So more than being a famous researcher, he is known for his teaching, the Feynman lectures, because he teaches things in a much simpler manner using very simple real world examples, and he will teach us the concepts of physics, even complex ones also, in a simple language. So he came along, he just gave a simple idea to the people, saying to the community, then you are searching in a wrong place. He said, you should not use a classical computer to solve the problems of quantum phenomena, right? A phenomena that happens at a quantum level, atomic level, those things need to be addressed or analyzed by a machine which takes that kind of a phenomena into the consideration. He may not said that the quantum computer is needed that time. He said that a machine, a calculator kind of a thing, if there is any, it should take the quantum phenomena into consideration. Then only you will be able to store all the data at a time or process the data at a time. So in a way, I will say he gave a spark towards quantum computing in 1960s itself. But his famous lecture in 1981 actually led to the breakthrough. Okay, so his quote is there anyway. He said, you better come up with a computer based on the quantum physics rules. It may be a quantum computer, it may be a universal quantum computer, and so on. That is the main spark. Okay, just I'm going through a little bit of history so that you would appreciate how quantum computing actually grown from the very starting idea itself. Okay, taking his idea and somebody started working on it theoretically. So in 1985, David Deutsch, he started building a model, a mathematical model, which is actually relies on a two-state system. Two-state system, for example, a simplest idea for a two-state system is just to take a coin, you just toss a coin. If you toss a coin, okay, what happens? If you toss a coin, coin goes up with heads and tail revolving.
Data.
Dr. Radha Sachan, please unmute your mic.
Yeah.
क्या करें, इतना काम का बोझ बढ़ गया है, समझ ही नहीं आ रहा क्या क्या करूं.
Dr. Radha Sachan, please mute your mic. Sir, you please continue. I will adjust.
Yeah. Okay. So, right. So what happened? Two-state system is just a two-state coin. Let's say heads and tails are there. If you toss a coin, what you see is head and tail revolving. See, this is a two-state system. If I catch a coin in the flight, what happens? It falls to one of the state. Right? We usually say the coin is a fair coin. In the case, it has a 50% probability to fall into one of the state. David Deutsch actually took such an idea, probabilistic idea, and he designed a kind of a theoretical model which can do small logical operations. Okay, so the binary operations he took. So in a way, he actually called this a universal quantum computer, which can be upgraded to higher dimensional system. As of now, let's say two-state system we started with. So which is actually of initial idea of quantum computer. Okay, we may not yet will know in detail what it is. Okay, we'll just go ahead and see how the things have progressed history-wise. Along David Deutsch in 1992, Richard Joyce joined along with him. They started working on computer, whether it's a theoretical model or experimental, some computer is designed, universal computer. On that, let's say I want to execute some task. Let's say I want to add two numbers, right? Or I want to multiply something. That's a repeated addition if I had to do. How should I go ahead on that mathematical computing model, how to do it? So for that, they came up with an algorithm, which is actually first quantum algorithm. They formulated it. So what they saw is a very good exponential speed up is possible with that kind of a computer, they realized. Okay, still at the theoretical level. So in 1993, Ethan Bernstein and Umesh Vajrani, these are the two people, they gave an algorithm, right, which is actually shows a possible significant faster computing capability in comparison to classical computers. Okay, so after David Deutsch and Richard Joyce, the next algorithm came. It is actually called Bernstein's Vajrani algorithm. It's in a way can overpower or like outplay the classical computing calculations. Okay, and this power is in such a way, the advantage is in such a way, even if you let the classical computer to have some small errors, okay, right, even in that case also quantum computers can outplay, means like they perform better than classical computers. That is what was seen till 1993. So let me go further and go ahead, show you or introduce to you people the two crown jewels of quantum computing, the algorithms wise, which is one is given by Peter Shor, a physicist, a mathematician. He actually gave an algorithm called Shor's algorithm. As of now, the Shor's algorithm is such a powerful thing which can be create waves in existing secured communication in the classical internet. Okay, what he gave is his algorithm can break the existing RSA encryption. You see, all the encryption which takes place in the internet, okay, right? Yeah, it is actually based on RSA encryption, where our passwords are linked to factoring a large prime number. You see, if I ask you what is the prime factors of a prime number 49, you can immediately give. If I ask you 81, you can immediately give. If I give a very large prime number, probably you might use a calculator or you might use a computer and so on. Let's say if I give a very large prime number, which is beyond the capacity of your existing computer, your personal computer or any supercomputer you may have, if the large prime number is so big, you might give up or your computers may give up finding a large prime factors. So that is the complex and hard task we can take, and we can create our passwords based on that large prime numbers. You know why? So even if your large prime number, let's say N here, which is public key, even though somebody get hold of that large prime number, the key, the password is actually in its prime factors P and Q. So no one can find out the prime factors. So that is how the RSA encryption is being designed to secure our passwords. So the banks may keep the passwords with them, or bank may give you a password to the individual customer, and the N may be there in the website or in the portal anywhere. The moment you type in your P and Q, the small prime number, large prime factors, the bank may take them and multiply them and find out whether it matches with the N which is reserved for your account. In that way, they will allow you to access your online account, for example, in the bank, or you can say some cloud access or any emails or anything. It is all simply based on RSA encryption. Okay, but if you take a Shor's algorithm, implement on a quantum computer, okay, this can find this prime factors of any large prime number in a very, very short time and a very, very less number of attempts. So that is going to create waves in the secured communication. In a way, it is said that existing RSA encryption is going to become obsolete. So that is why there is a dire need for us to go and understand how quantum computing works, how especially the Shor's algorithm works, how to tackle the problem the Shor's algorithm may induce. You know why? Not everybody is honest, not everybody is good people. There are imposters. They may use Shor algorithm and they may get hold of some quantum computer. If they happen to use, definitely they can hack into your secured login IDs, whether it's a communication or it's a financial things. Anywhere it is going to be vulnerable if they get hold of a quantum computer and Shor's algorithm. Okay, so that is about Shor's algorithm. Let's see, this has come in 1994. In 1996, Low Grover, one of our Indian graduate from IIT Delhi, he went to US and in 1996 he gave an algorithm called Grover's algorithm. In a way, it is a much powerful algorithm. Why it is so powerful is, if I have, let's say, a set of numbers, let's say 0 to 1, 2, 3, 4 up to 9, let's say I have a numbers. Okay, if they're arranged in an increasing order, okay, if I have to pick 7 from that number set, so if it is arranged in an increasing order, if I had to pick the 7, if say they are hidden inside some boxes, individual boxes, what I will do, I just go to the particular box 7, counting from left hand side to right hand side. I'll go to 7 and pick it in first attempt itself. Let's say if somebody has arranged in a decreasing order, probably in that case, my first attempt I might fail. So in the second attempt, what should I do? I count from the right side to left side. You know why? I already know that the numbers are arranged in a orderly manner. Whether it's increasing or decreasing, for sure. Since the first time I tried with the increasing order, I failed. Second time I try with the decreasing order, I will definitely find out. So in just 2 attempts, I can find the numbers, the required number from the data. Now the question is, let's say if it is not arranged in any order at all, they are arranged or they're just shuffled so that they're in a jumbled fashion, it is there. So in that case, you know, how many attempts required for me to pick a 7 out of these 10 numbers? If I see on my best day, yes, on my lucky day, I may get in first attempt itself. That is there. But I should also look for the case of where the situation is the extreme case, large number of attempts. Means on my worst day, what can happen, you know, up to 9 attempts, I may not get that 7. At the 10th attempt, I may get the 7. So that is something which I am not sure of having such a kind of iterations while picking a given number. Okay. So even in that extreme situation of jumbled or not at all oriented or ordered structure in the data, if you happen to use Low Grover's algorithm, what you can do, you can just pick the required number with a very, very less number of attempts. How many attempts? He says, let's say the data size is n. You can pick up the required number in the square root of n's attempts. That is a quadratic speed up. Let's say the 9 numbers are there roughly. I'm just not taking 9, 10, I'm just taking 9. So in just 3 attempts, you can pick the 7 out of this 1 to 9, exclude the 0. So in that case, you can pick. Okay, so that is a commendable thing in comparison to existing classical algorithms. Yes, in case of classical algorithms, there is a algorithms which can allow you to pick number in unstructured data, but it may require a more number of steps. Roughly saying, if there is a size of the data is n, so you might need n by 2 attempts or something of that sort, but definitely not a square root of n attempts. So the quadratic speed up is something, is again giving a very, very good punch to the existing classical algorithms when it comes to quantum algorithms. Okay, so let me go further. Right, so in 1996, the motivation for going for quantum computing is studying the biological process like a photosynthesis. In 1996, Seth Lloyd was able to propose algorithms which can simulate the quantum mechanical systems, like say photosynthesis process, how exactly the plants can go and get the very good efficiency in converting sunlight into the required energy for the plants. Okay, so this is all simulations work in 1996 happened. So the objective is satisfied. How it is done, I'm not going to the details in 1 hour time, so we'll just jump over to the trends just to see the research trend starting from 1980s, from the spark of Richard Feynman, the initial decade or decade and a half. What you see, the research wise, quantum computing is not healthily. So later on, you see a very good increase from 2000 onwards. For the past 20-25 years, amazing research increase and the technology advancement has happened. Right? So for the past 3 to 4 years, we are hearing a lot in the news because of the advancement in the technology in the quantum domain. Okay, so the publications also there. This is the data from 2021. So if you just take the recent 4-5 data, it will again have a very good steep improvement. Okay, so that is the history for you, and you will really appreciate looking at the history. Why do we need to go to quantum computing? Is there is a requirement more than a need. Okay, for the communication perspective, you have to secure your communication. With the RSA encryption being obsolete, there is some other alternative means should be looked at, and for that you should understand what would be the threats from Shor's algorithm. Okay, so having that motivation, let's quickly take how quantum computers work in the first place. Okay, so I'll start from a very simple idea of quantum memory. Okay, just to understand a quantum memory, we will take some kind of a background knowledge of our existing classical memory. We all know we use a hard disk inside our computers, which stores the binary information 0 and 1. Okay, the question is how they store it. So some of you physicist people would really appreciate, which is actually uses the idea of magnetic moments. Okay, what is magnetic moment? If I just take a simple atom, okay, a conducting atom or an atom which can respond to external magnetic field, if I just take that, you know what happens? It has a valency electrons, unpaired valency electron. Even though there are other electrons inside the valency orbit, they are not going to contribute anything at all. You know why? They are actually compensated or they will be neutralized by the protons inside the nucleus. Only the electron which is there on the outermost valency cell, that is going to contribute. That is where the main magic happens, because the metals, or I say conductors, are the ones which are going to have a valency electron. They are unpaired electrons. They are going to create a lot of magic by creating some kind of a current through the wire around that orbit. Okay, so let me quickly use my handboard note. So I'll explain what it is, what I meant. Okay, right. If you just see, if I have a current carrying wire, okay, if I have a current carrying wire, let's say current goes from bottom to up, a DC current, you can simply say around that wire there is a magnetic field is created. Very simple. Okay, so you just take a right hand thumb rule. From the thumb rule, thumb would show the direction of the current, your fingers would show the curling fingers would show the magnetic field lines. Now what happens if I have a straight current carrying wire? I'm not going to have a single current carrying wire. What I will do, I'll turn that into a ring. That is possible. Okay, let's say this is how I'll have one of the lead is connected to one of the battery, another lead is connected to small terminal battery. Okay, now what happens? A current actually constituted in this ring wire. Everywhere there is a magnetic field. You see, the magnetic field is there. Okay, and interestingly, all these magnetic field lines are going to add up inside. They're going to cancel outside. Okay, so because of that, what you see is the magnetic field lines comes out and gets in. Magnetic field side comes out and gets in. If I have to show the direction of magnetic field lines, there will be something like this. Okay, and if you want, just know, I just said electric field lines, current magnetic field lines cancel. What I see is there is a very strong magnetic field movement is created inside. Okay, means magnetic fields are coming out, entering from the bottom. So what is this is just a simple bar magnet. So every current carrying loop of an orbit, valency orbit, is equivalent to a bar magnet, north and south. So for us, bar magnet is just a magnetic field lines starting from north pole, ending at the south pole. Okay, so an electron which is revolving in an orbit is equivalent to a small bar magnet. So people took this idea in a small magnetic strip which is responsive to the external magnetic field. I can arrange all the magnetic moments of individual atoms pointing towards the south, north, south, left is north, right is south. If I arrange them, let me call it as 0. If I arrange it opposite, I will call it as 1. So in this way, information is fed out to the magnetic strip, you see. Okay. So, 1 minute. Yeah. Information is fed onto the magnetic strip. And if I have to read it, I can read it using another small magnetic field reading head. From there, I can just read it. If I have to store the information more, I can choose the lateral version of it. But somehow, this is how information is fed onto a magnetic strip. Let's say a hard disk, right? Whatever we have, in that the magnetic moments can be aligned in a particular direction. If I had to count how many number of magnetic field lines are involved, magnetic moments are involved, there is a plenty. Okay, a lot of them will be involved. So the question is, how many electrons or how many atoms are involved? I would say billions. But for sure, they are very certain to be aligned in a particular direction. You see, they're all arranged in a left, north, south direction. Okay, fine. This is how classical memory works. And there is a optical memory that is also there. For the discussion point, let's ignore that. Let's see how quantum memory works. Having many atoms are involved in a classical memory. Now, when it comes to quantum memory, hardly very few atoms are involved. How? Very simple. You just take a nucleus, a simple nucleus, and surrounded by orbits. Let's say only one valency electron is there in that particular atom. What people thought is, let's say the electron is there, you supply a photon of energy. You know why? This is tied to the nucleus with a Coulombic force of attraction. In order to move this electron anywhere away from the nucleus, you have to supply some energy. It's like some kind of a thread is there. You have to stretch it like an elastic thread. If you stretch it, it will go away. So the Coulombic force is like a thread. If I supply some energy, you can do it from any means. You can just supply the energy in terms of heat, in terms of in terms of collusion with some other means, or you can supply a light. If I supply a light of photons, trick here is the energy of the photon must match with the orbit's separation. If I do it, I might see the electron just excite to the outermost orbit. Now, that was the assumption, our intuition. When I supply a photon of energy, we think that electron would jump by consuming the electron, so that the photon, they may come to the external orbit. Okay? So that is a simple logic, right? If I give a nice chocolate to a kid, we assume that kid would immediately eat. Okay? So that was our intuition here. We assume that electron would consume that photon, would jump to the outermost orbit. Okay, but the thing is, if I ask, let's say 100 of my students to take this 100 atoms and do the experiment with 100 photons, I'll ask them, please report to me what you observe. Out of 100, interestingly, some 60% of them tells me excited, and 40% of them tells me the electron is not at all observing the photon just comes out as it is. They will just tell there is some problem with my equipment or something, they will say, but there is no problem whatsoever at all. Why this is? Because at a quantum level, I would say at atomic level and a subatomic level, things are not certain. Means they all becomes probabilistic. Probabilistic in the sense they may have some time observe, they may not observe. Who tells? We don't know. As if they have their own mind, they will observe or they may not observe. Okay, so just to put this into the context, put it into the description to somebody, I need to use the notion of probability. What is this probability? It tells me if I shine a photon onto an atom with a valency electron, single valency electron, there is a chance of electron may get excited. There is a chance of electron not excited. Okay, so that means if I just to experiment with one single photon and single electron in an atom, I have a chance to create two numbers on that system. One is probability 60%, another is probability 40%. Let's say I may not work with single atom. You know why? If I give a coin, if I toss a coin, if I catch a coin after the toss, if I ask what is the chance of I'm getting heads, you would say 50% of the chance. But if I open it, let's say I see heads, I'll just contradict to him. I got the answer. I got the heads with 100%, right? So that is not the way the experiment should be performed. When it comes to a coin, you should perform the experiment 100 times. Out of 100 times, you have to catch 100 times and see what you get. There you will see 50% of the time heads, 50% of the time tail. You see that is the probability of fair tossed coin. Same here. When I say a photon is shined onto an electron, the electron may observe or may not observe. It is all becomes a probabilistic in nature. That means this number 60 and 40% can be stored on this single atom. Okay, may not be single atom, at least few hundred of atoms can allow me to store 2 bits of information in terms of probability. Then I am through. You know why? Here if you see, billions of atoms are required to just to store one single bit 0, single bit 1, because there is a lot of atoms are involved in a small strip. Okay, so that is where the quantum computing is going to a step ahead when it comes to memory storage itself. Okay, so just this take home here is a few atoms, or I say a single atom can allow me to store 2 bits of information in terms of its probability. Let's see what is that in the next slide. Okay, right? So from the physics point, I just want to give a description. Why is that so? Why a probability is there when it comes to electron excitation? Why it is not certainly happening? So to answer that question, we can dig a little bit deep into the physics. What is that physics says? At quantum level, things are not clear. It is all ambiguous. It's all fuzzy, because as I go to a smaller objects at a microscopic level, what happens? I can't exactly specify the location of an entity. For example, if I just take an electron, I can't exactly specify its location with 100% accuracy. If it is moving, I can't exactly specify its mass. Sorry, I can't specify its velocity. If I multiply velocity with the mass, I'll get a linear momentum. There is always, I make a mistake of position error, mistake of momentum error when I try to find the electrons position and momentum with the accuracy. So that is actually Heisenberg uncertainty for you. So what Heisenberg says, there is a delta x error, delta p error, which is always going to be more than Planck's constant when it comes to find an error, find a position and momentum of something which is moving at a quantum regime. Okay, so because of that, you know what happens? Things are fuzzy. Okay, so let me take a simple example and understand what is this fuzziness is all about. Okay, so let's take a one-dimensional box. One-dimensional, what I mean is, if I let something inside a box, it can only move left and right. There is no other way to go up and down or any other direction. Let's say if I just place an electron inside that box, okay, and later sometime if I notice, I see electrons moving around here and there. Okay, I understand probably electron is so tiny quantity, it might take energy from the surrounding weather, surrounding temperature, and that gives its energy to move around. Okay, so what I'll do, I'll reduce the temperature, let's say absolute zero. Means there is no ambient temperature to supply the energy. Then again, if I see electron is again moving around, so that means I assume that there may be some other particles which are colliding. They may colliding and giving energy. Okay, let's say this side, I'll make it a vacuum. So except one electron, nothing is there inside this one-dimensional box. Now, if I let the electron to stay inside a box, if I start observing where is this electron is located, okay, I see it is not standing at one point. You know, when I place a pen on my desk, it stays there until somebody comes and disturbs it. That is because of the Newton said it's in the inertia of rest. If something is moving, it can move continuously until somebody comes and disturbs because of its inertia of motion. But here in this case, interestingly, the electron, irrespective of the temperature around, irrespective of nobody is there around, it still moves around. What happens? It moves around. Then let's say I make several thousands of observations and find out where is this electron is located in a given time. If I try to find, let's say in a position, let's say position along x direction, if I find out, interestingly, what I see, the electron presence is showing some kind of a distribution, probability distribution. What I mean is, it shows some kind of a distribution where the electron exists, okay, maximally at some point. So there is a maximal distribution at some point. Okay, wherever there is a peak here in the hills, the electron is maximally existing, and at some locations electron is absolutely zero. Its location is not at all same, zero. Okay, and at the walls is zero anyway. Electron cannot exist. This is what people saw, or somebody does the experiment, they see. This is a probability distribution for you. Now, why is this so? It's supposed to stay at one place. Why it is deviating or moving? As the answer comes from the property called wave nature or wave duality. What is that is? If I just take, let me call this some function, let's say, let me call this function some g, and you just take a square root of this g and try to plot, take positive and negative quantities, and if you plot it, what you see is, okay, let me take a different color, 1 minute. Okay, so if I plot it, interestingly, a square root of this function comes something like this. Okay, something of this sort. Now let me call this a function f, and what I mean is f square root of g is f, and I take a positive quantity here and the negative quantity here, square root of something is positive and negative. Okay, so there is a mathematical function. It is like some kind of a wave. If I tie a rope at between these 2 points and create a small wiggle, that disturbance travels along the wave and comes back and creates a standing wave pattern. This is some kind of a wave. Now the question is, if I ask someone where is the wave located between these 2 points, they will straight away say wave is located everywhere. Okay, so the question answer is everywhere. Similarly, okay, the absolute square of
I think, sir, your voice is not coming. Just I think, sir, your voice is not coming.
I think somebody muted it.
Okay, no issues. Please continue, sir. Again, your voice is not coming, sir. Yes.
Hello?
Yes, sir. Now it is coming.
Yeah. Ma'am, I'm in a class. Can I call you after? Okay, thank you. Can you hear me, ma'am?
Yes. We can hear you, sir.
Okay. I think my meeting, like a presentation got exited, I guess.
Yes.
Yeah, I'll just share the screen again. Yes. So
yes.
What I was talking is, if I put an electron inside a one-dimensional box, it is going to have a probability distribution, means its presence at different points in a probabilistic manner, some kind of a hills. Okay, so just why is that so? People started understanding and they started connecting this to a wave nature. It's like a wave, a thread is connected between these 2 points, create a small wiggle. The wiggle goes everywhere. Okay, so that wiggle goes everywhere like a standing wave pattern. And now you take that wave and square, absolute square, you do it, that exactly matches with this probability distribution. Okay, so what De Broglie said at that time, he said, let's take a very small object like an electron. If I put it somewhere, okay, it is going to show some wave nature, some kind of a wave disturbance. What is that wave disturbance is? It is going to have a wavelength lambda, which is equal to Planck's constant divided by mass into velocity. It's a linear momentum. Okay, so if the mass of an object is so small, if it moves with a velocity of close to the light, what happens is this object can exist in the waveform. That waveform would also allow you to find its probabilistic location. Due to this, there is a explanation. We can understand, okay, why the electrons are moving around. They are moving around because they may have some internal energy, the 0-point energy in the first place. Because of that 0-point energy, they move in such a way, right? They exist at some point with a maximum probability, at some point no probability at all, which is equivalent to having a wave kind of a disturbance. Okay, so conclusion here is, do particles possess some kind of a wave nature. Okay, every particle in the universe is going to have a wave nature. Even we do have a wave nature. It's a very bold statement to make, but only problem with our wave nature, right? So if I had to calculate what is a wave nature or a wavelength associated with a wave around me, is going to be much smaller, wavelength wise. The mass of a human is very large. Velocity can't be more than meter per second. Okay, a Planck's constant here you see in the numerator is -34. In the denominator, whatever number you are going to put for classical object, the overall lambda d comes out to be very small, which is about 10 to the power of -25 meters, which means the wavelength is so small you can't measure that kind of a wavelength. That's why we ignore the wave nature around us. But when it comes to a smaller and smaller object, for example, moving bullet, definitely you can calculate some wavelength, which is about something around 10 to the power of -18 to 10 to the power of -20. Okay, if I go to smaller and smaller objects like electrons, okay, for them the wavelength comes out to be an optical frequency, something around -10, 12 to -15, which is easily measurable. That is where everything happens. Okay, so if there is an electron moving in an orbit, you can just straight away think that there is some kind of a wave nature created due to this electron. Okay, it's simple analogy for this would be, you go to a lake nearby, a water body, you just throw a stone. If I just throw a stone, you know what happens? Okay, if I just throw a stone, it creates a wave, like a ripples it creates. You see where the ripples are located? Initially, your intuition says ripple is there at the center where the stone has hit. It's no. The stone creates the ripple. The ripple is there everywhere. It travels around the entire lake surface. Okay, so that is a wave nature for you. Electron is some kind of a ripple creator. Once the ripple is created, it says it's a ripple, a wave stays everywhere. So let's say if there is a valency electron is there, it has created a ripple around, there is a wave around. Okay, right? So what is the wavelength? You can easily calculate knowing its mass and velocity. Okay, and in an atom, if there is a lowest orbit, it may have particular kind of a wavelength. What kind of a wavelength? There may be one single wavelength confined in that particular orbit. Okay, a second excited orbit, maybe 1.5 or 2 wavelengths, and so on. Depending on the length of the orbit, you may have wavelengths confined in that orbit. So this is the idea of quantum ambiguity. Particles by nature, their material, they are going to show wave nature. Okay, interestingly, if I just take a wave, they will show the wave particle nature. So that is where people call wave particle duality from the physics point. For example, if you take a photons, they are the light particles, right? So they are the energy particles. They behave like a particles when I see light with a high dimension, high definition. Okay, right? So now coming back to the quantum memory. So if there is a particle confined, let's say an electron in an orbit, it can show a wavelength, something like that, and its corresponding probability distribution is absolute square of wave function would show some kind of a hill. Now people took this idea and they started creating some kind of a memory out of any two properties. Let's say if electron can exist in two kinds of a wavelength, very simple. Let me skip the Schrodinger equation and the description. How do we look at the question is, how do we get this wave nature for a given an electron in a particular orbit? Very simple. You take a Schrodinger equation. In a way, it's a Newton's kind of a second law. F is equal to ma. For any classical object moved around by a force, you define with the F is equal to ma. Similarly, if there is a quantum particle confined in a potential, okay, right, it can exist with various wave natures like this, okay, with the corresponding energies, okay, and which is actually going to show a satisfaction for Schrodinger equation. Okay, so this Schrodinger equation, if I solve, it is a sinusoidal function. If I plot the sinusoidal function within a particular boundary values, I am going to get such a wave equation, and I take the absolute square of it, and then I can get probability distribution for a particles like electrons. Okay, right? So coming back here, for a 3-dimension, you will get orbits. Okay, so you get orbits. Maybe there is some resound or something. Let me see. 1 minute. Trying to reconnect my call. 1 minute.
No issue, sir. You can do it.
Madam, are you able to see my screen? What I'm writing?
Yes, we are able to see. Just now it stopped. Now it is visible, sir.
Now it's visible. Okay.
Yes, yes.
Yeah.
I think now your screen is stopped, sir. I think sir is unmuted. Check it.
Yeah, I forcefully it is getting muted. I don't know why. But I'm trying to share with my system. Are you able to see some screen?
Yeah.
And
Yes. I am able to see, sir. Sure. Yes, it is coming your screen, sir.
I'm just scrolling down, right? That one.
Yes. It's a single qubit quantum gates is written, and
okay,
qubit.
So I think my tab got somehow exited. So I'll just use the personal computer itself. Okay, so here if you see, they took atom and its orbits and started realizing quantum memory out of it. They call it as atomic memory. How it is done is, we just take two orbits, okay, call it as the lowest orbit a ground state, another orbit is the excited state. And like I said earlier, if I shine a photon, the electron may jump and may not jump. If it jumps and stays there for 1 microsecond and comes down, and while coming down, it emits whatever photon it got absorbed in the first place. Okay. And interestingly, here there is a probability involved, probability of excitation and probability of not excitation. Those are the two numbers people started using to store 2 bits of information on a single atom, or at the most few atoms per se. Okay. So this is how quantum memory is realized. One advantage with the quantum memory is with a few atoms itself, I can store 2 bits. Okay, so that is a quantum smallest bit storage entity. In short, it is called quantum bit or qubit. Okay, right? So what it's consisting on paper, how to represent that? Very simple. I would say it's something to do with a quantum state. Let me write down a Greek letter quantum state. Psi is equal to 40% of the time the electron is not excited. I would say one state. Another 60% of the time it is excited, another state. For a same electron, there are 2 possibilities of not exciting and exciting. Let me write down in that way. Okay. Why I'm writing in that way? I want to make it more sensible to convey the idea of excitation, not excitation to someone. But the problem here is, if I see, by the way, what is a wave function for me? It's a sinusoidal function, classically. Okay, so it's a function something of psi is equal to some cos of kx minus omega t, where k is propagation vector, 2 pi by lambda, and then omega is angular frequency. And if I take absolute square of omega as a psi, I should get a Hill kind of a probability distribution. That is where I find the electron location maximally at some point. Now the question is whether the whatever state I have written here, is it exactly conveys and matches with this wave function, actual wave function? Absolutely not. So to make it more sensible, what Dirac did, he introduced a notation called Dirac-Ket and Bra. What is a Bra? Ket is, together it makes a bracket. He said, let me call a quantum state psi as a psi ket is equal to some not excited state plus some excited state. He has put some probability, some kind of a proportionality constant alpha and beta, where absolute alpha square and absolute beta square, they are the ones which represents the probabilities. Okay, in that case, alpha and betas are actually probability amplitudes. It's just like any probability, any amplitude of a electromagnetic wave. You see, electromagnetic wave is represented by E equal to epsilon E naught into cos or sine, right? Just like kx minus omega, where E naught is an amplitude. Similarly here, the psi is equal to amplitude alpha multiplied by not excited state plus beta excited state. Okay, so amazingly, the moment you put this kind of a notation for this quantum state, everything falls into the groove. What is that groove? You take absolute square of this sign. Okay, right now let me say not excited state is 0, excited state is 1. In that case, I'll write in a short form psi ket is equal to alpha 0 ket plus beta 1 ket. What is a ket? Ket notation is just like a vector. Okay, it's just like I vector and j vector in two-dimensional Cartesian coordinate system. A position vector is written as xi plus yj. Similarly, quantum state psi is a vector r. Okay, I cap is just like a quantum state vector 0 ket, and j cap is vector I ket. Okay, now the catch here is, as we know, absolute alpha square, absolute beta square must sum to 1. You know why? I am not leaving the electron to go anywhere other than these 2 points. Means its presence should sum to 100% within these 2 orbits. So that constraint we are going to put, absolute alpha square is equal to absolute beta square is equal to 1. Now, if I just see this, the resemblance or some kind of analogy between quantum state to Cartesian vector R is, Cartesian vector is defined on a base of I and j, and here the quantum state is defined on a base of 0 ket and 1 ket. Okay, for me, Cartesian coordinate system base is not just any base, it satisfies some kind of a relation where the dot product is the operation, I dot I is equal to 1, j dot j is equal to 1, I dot j is equal to 0. Okay, so the question is there a such kind of an operation or a conditions exerted on 0 ket and 1 ket so that there is a one-to-one correspondence between a quantum state vector psi ket to a Cartesian coordinate vector r? If such a thing would appear or exist, it should have some operations like this, what is shown here. Here, I say there is an operation between 0 ket to 0 ket, which should give me 1. 1 ket to 1 ket should give me 1. 0 ket to 1 ket should give me 0. That is the requirement, just to have a one-to-one mapping between quantum state to quantum state vector to classical state vector. Okay. Now, for that, a matrix interpretation would answer. What is that matrix interpretation is? Let me call a quantum state vector 0 ket as column vector 1 0, 1 ket as 0 1. Okay, Why I'm only playing with the 0 and 1 here is all the system, what I am talking about, it's all about binary system. There are only two numbers for me, 0 and 1. There is no other way I can have any other number. So I have to play with the 0 and 1s. So I'm calling 0 ket as a 1 0 column, 1 ket as a 0 1 column. Now what happens if I take an operation between 0 to 1 or a 0 to 0? It's a matrix, you see. It's a dimension of this matrix is 2 by 1. I can't multiply two matrices of same dimension. I need to do some kind of a matrix order matching so that I can create a multiplication. Okay. For example, I want to have a multiplication between 0 to 0 ket. What should I do? Let me take the left hand entry of 0 to 0 multiplication here. Okay. And take the multiplication to the ket. Convert that into a bray. What is a bray? Is a transpose of a ket is a bray. Transpose of a column, okay, is a row. If I do it, the order is going to match now. You see the order of this 1 0 is 1 by 2. When I have a 1 by 2 matrix multiplying to 2 by 1 matrix, it is allowed. I am going to get 1 0 row multiplying to 1 0 column, giving me the 1. So I got what I need. What I need, multiplication between 0 ket to 0 ket is giving 1, provided the left hand entry of my multiplication is going through a transpose and then getting multiplied to the right hand side entry. So if I do the same trick, I will get 1 to 1 multiplication is 1 ket. Sorry, 1 ket to 1 ket multiplication is 1. 0 ket to 1 ket multiplication is 0. Okay. So which means whatever required operations I got realized here, provided I take the left hand entry to be transpose and the operation is matrix multiplication, just like a dot product in the case of Cartesian coordinate vector space. Okay. Right. So by doing it, what we can achieve is we can represent a quantum state in terms of a column vector with the probabilities taking the numbers in the vector. So here, if you substitute a 0 ket in terms of a column, 1 ket in terms of a column, you would get quantum state represented as alpha beta, which is a column vector 2 by 1 dimension. If I take its bra, or a transpose of a ket, is a column vector where alpha and beta are becoming elements of a row. Please remember, I should have a alpha star and beta star if my alpha and beta are complex numbers. Okay, I cannot just take only transpose. I should also add a complex conjugate, because the matrix multiplication defined in the case of quantum state vector to vector multiplication is adjoint, not just a transpose. You also take a complex conjugate. Okay, right? So this is how a one-to-one resemblance between a state vector of a two-dimensional surface is given to a quantum state, which is a complex vector space. Okay, so people call it as a Hilbert space after the Hilbert, where the vector space is defined on a basis of 0 ket and 1 ket. They are the unit vectors. You see why they are the unit vectors? If you find out length of this column vector is 1, length of the 1 ket column vector is also 1. So which means their length 1 normalized, then they are orthogonal, they are perpendicular to each other, their inner product is 0. So in that way, I have a very good one-to-one resemblance or a correspondence between the classical vector space to a quantum vector space. Okay, so why this vector space is required? Using this, I can give a very good geometrical interpretation for all my quantum states. How? Very simple. I can convert alpha in terms of some polar angle, beta in terms of polar angle, as well as azimuthal angle of a three-dimensional polar coordinate system. In that way, I can define the probability amplitude on the surface of the sphere, which is actually called a Bloch sphere. Okay, so what is the Bloch sphere use is, I can represent a 2-qubit quantum system, that is a qubit on the surface where it's a two-dimensional surface. Basically, polar coordinate system, three-dimensional polar coordinate system is going to have 3 dimensions. One is r, the distance away from the center, and polar angle. A vector makes a polar angle with the north pole, and there is a azimuthal angle created by the shadow of the vector in the equatorial plane. So that is another dimension. So for example, if I just take a north pole, means theta is equal to 0, I will get contribution only on the 0 ket. I'll not get any contribution from the 1 ket. You know why? Theta equal to 0 means sine 0 is equal to 0. So I'll not get contribution from 1 ket. So you can say the north pole of a block sphere would represent a quantum state being in a ground state. Okay. If I take a theta is equal to 180 degrees, that is a pi radians. If I substitute pi radians here in terms of alpha and beta, I'll get beta is equal to be 1, alpha equal to be 0, because cos pi by 2 is 0. So I'll get a contribution from only 1 ket. So I will say the south pole is having quantum state 1 ket, which is an excited quantum state. Okay, right? So any other point other than north and south pole, you see quantum state is distributed between 0 and 1, which is like a quantum state or a quantum system hopping between ground and excited, or it is creating a superposition of 0 and 1. It is just like a fuzziness being created. Either atom excited or not excited, we never know. It is all probabilistic in nature. That is where I use a block sphere representation to represent that. So one simple example is I can show a quantum system being equally superposed, like a 50% in the ground, 50% in the excited, which is on the equatorial plane, just by rotating a given quantum state initially in the ground state, rotating it that by pi by 2 degrees, I can show a quantum state system is being put into a superposition state. How it is done? It is in terms of some kind of a pulses of photon are coming in and interacting with an atom in the ground state, putting the atom into the excited state and superposition state, ground and excited superposition with a pi by 2 pulse. Okay, right? So that is a pi by 2 pulse people would execute in the experimental lab. Not only that equal superposition along the x-axis we have, there is equal superposition on the minus x-axis and the y-axis and minus y-axis. Any point on the equatorial plane would represent equal superposition of a quantum state being in the zeros and ones. Okay, right? So the another question I can do is, am I satisfied with a single qubit? Absolutely no. We need to do a lot of information processing. So in that case, I need a higher memory, not just a 2-bit memory. I need a higher memory. How to create? Very simple. You take one atom being in superposition of 0 and 1, another atom being in superposition of 0 and 1. You put them together. It's like a two atoms in the same box, or 2 electrons in the same box. Okay. When I say 2 electrons, what I mean is each electron can exist in 2 states or 2 orbits. I'm only seeing from the perspective of 2 electrons. One electron in 2 states, another electron in another 2 states. If I put them together, mathematically I can show them with a tensor product. Okay. So what this mathematics would represent is 2 atoms are just coming together and trying to interact with each other. Okay. They may interact, they may not interact. Let's say they start interacting. There is a possibility of having more states. What are those more states? 4 states here. 2 systems with 2 individual states combining, creating 4 states. Okay. One is both of them in the ground. Other one is both of them in the excited. Other 2 are one of them in the ground. Other one is in the excited. So this is how you can create a quantum state, 2 quantum system, creating 4 possible states for you, which is represented on a paper using this quantum superposition state and a tensor product. Okay. You see here the basis now is a 4-bit basis. Earlier 2-bit basis we have. 2-bit bases are combined and creating 4-bit basis. Okay, right? So what are this 00 ket would be represented on paper? It will be a column vector of 4 elements. You see, and you can go on. You can have higher dimensional quantum system by just combining multiple qubit system and creating higher and higher dimensional bases. Okay, right? Okay, I hope you people are able to hear. Right, yeah, fine. So in between, I had to cross check. Okay, so this is a quantum higher dimensional system. Now, having information, how do I process the information? Okay, first thing is, in the classical computing, we have gates. Okay, so we have gates. So from the gates, we process the information. Now, first gate comes to our mind in classical computing is a NOT operation. The question is there any NOT operation in classical quantum computing? Yes, there is. If there is one, what expectation I have here is, I want to convert a basis 0 to 1, 1 to 0. Okay. So in quantum computing, the smallest entity is a qubit, a 2-bit superposition system. If it goes through it, what I should see, 0 becoming 1, 1 becoming 0, which means if you carefully see, the alphas and betas are just interchanged. The probabilities are just interchanged with that NOT operation. Okay. Since I'm talking in terms of matrix operations, so for the NOT gate operation, what is an operation? What is a matrix that interchanges alpha beta from beta alpha, which would be a simple matrix, which is a 2 by 2 here, which is just a 0, 1 and 1, 0. By trial and error method, you can get that matrix. Okay, that matrix is called a X matrix or a X gate or a Pauli X gate. Okay, right? And interestingly, what you see here is alpha beta and the resulting beta alpha are also going to satisfy their absolute square is equal to 1, which means you can say the information is preserved. Okay, the quantum vector length is preserved through the quantum gate operations. Okay, and more than that, there is some interesting factor or feature associated with this X gate here is, if you take that gate, take its adjoint and multiply it with itself, what you get is an identity. So what is this gate is actually called, with the mathematical physics, it's called a unitary gate. Okay, so only unitary gate gives such kind of a norm preserve, norm in the sense length is preserved through the operation. So a quantum gate here, the X gate is unitary by nature. Okay, let's see, is there any other gate for us? In quantum computing, yes, there is one more gate where in the superposition, there is a positive parity in both alpha and beta. I can introduce negative parity. Okay, so if at all, if that kind of a gate is required, what that gate, again by trial and error method, you can find that is 1, 0, 0 minus 1. If I have that operation or the gate operation on the quantum state alpha beta gate, what I will be getting is alpha minus beta. So basically what I'm trying to do, I'm inducing a relative phase between alpha and beta. With relative phase means exponential I pi, radian pi, would introduce minus I at this beta. Okay, this is called a Z gate or a phase gate of pi. Okay, so it's a Pauli Z gate is represented. Okay, having a X gate and a Z gate, we can create another interesting gate called H gate or a Hadamard gate. What you do, you take a X and H, Z, and add them. What you get is 1, 1, 1 minus 1. Okay, and by nature, quantum gates has to be unitary in nature. So just to ensure that gates has to be unitary, you put 1 by square root of 2 multiplication. In that way, you can create a quantum unitary gate with the X and Z together summed up. Okay, so this is a Hadamard gate for you. And what is a Hadamard gate action is, if you act Hadamard gate on 0, you get a superposition state which is equally superposed. Okay, so that is what we saw in a block pair representation here. You see, if I have a quantum state is pointing towards the north pole, means the atom in the ground state, if I shine a pulse of photon with a pulse area of pi by 2, what I will get is the quantum state being rotated from 0 ket to x direction, where equal superposition is there, which is actually a Hadamard operation. You see, Hadamard operation. So with this, what you can conclude, we just saw X operation, we saw Z operation. What you can conclude is all the quantum gate operations are in a way rotating about some axis. If I put the rotation on a single two-dimensional vector, two-dimensional surface, I would see quantum state pointing in one direction is getting rotated into another direction by taking a superposition state. Okay, so all quantum operations are some kind of a vector rotations. Okay, right? So those are the single qubit gates. You can have multi-qubit gates also, which is something called a control not operation. What is this control not operation? Is some control is there. Based on the control, target would be manipulated. If the control is 0, target would be left alone. If the control is 1, target would be flipped. So this is a control not gate. Okay, so just by ideology of target controlling the manipulation, you can write down some kind of a truth table. And if you see for the C0 operation, okay, you just compare inputs to the target, what you see, some kind of a XOR operation, right? Exclusive OR operation. So you can say C0 operation is some kind of a XOR operation. You can even represent C0 between two quantum registers A and B is equal to register A, which is control left as it is, but register B or the control register is manipulated by adding a control A to that. So B plus A is the addition modulo. Okay, right? So that is what you see in the target output. So
Dr. Aswath Babu? We will wait for a speaker. I think he's just rejoining the session.
yeah, hello.
Hello, yes, sir.
You lost me in between at the end?
Yes, I think 2 minutes or 1 minute before.
Okay. I'll just conclude. We can continue tomorrow. Okay.
Yes.
So here, if you see, this is C0 gate for you, and its operation can be shown on a paper like this. Okay.
This slide is not coming, sir.
1 minute. Okay, share. Can you see right now?
Yes. No, yes.
Yeah. So one interesting thing with the quantum gates is it's all reversible in nature. What I mean is, you take any classical gates, the input information is destroyed to produce the output information. So you never able to recollect or recover the old information from the output. But when it comes to quantum gates, you can always recover the old information or the inputs, I mean. So the reversibility is a very, very handy tool to debug the quantum information. Okay, right? So one interesting thing is you can create an entanglement using quantum gates here. Okay, so this is all we see as a part of quantum algorithms in the tomorrow session. I'll just stop at this point. Let me conclude. We just saw how quantum memory works. Okay, right? Having the quantum memory, we can represent that quantum memory as a quantum state vector, which is equivalent to a two-dimensional vector. How to process that vector using quantum gates we saw, right? So not only just single qubit, there are non-trivial 2-qubit systems or gates are also there. Using that, we can create some kind of a correlation or some kind of a mutual effect between two quantum resistors. Using those quantum resistors and the mutual effect creating gates, we can do a lot of interesting stuff like entanglement that we will see as a part of quantum algorithms in the tomorrow session. Okay. right? So I will stop at this point and I will hand it over to the organizers. Divya ji.
Thank you, sir. First of all, it's a very easy way. I think I never saw somebody teaches quantum computing. It's so much ease. I think for the participants, it's a very excellent opportunity to learn about the quantum computing, the basics and fundamentals of quantum computing. So thank you so much, sir, for teaching us with very patiently. Thank you so much, sir. Now I will take questions from audience. Please, participant, put your question.
Thank you, sir.
Participant, you can ask your question on WhatsApp or this message link. Okay.
Yeah, if there is any questions, you can share with Divya ji. Tomorrow also we have a session. I can.
Yes, please. I think today, yes. No issue, sir. I think we will further continuing this session tomorrow morning also. Okay, participant. Sir, thank you, sir. Thank you, Aswath Babu, for sharing your knowledge with us. I know this is for a beginner at quantum computing, it seems like a very little bit on tougher side. What do you suggest, sir?
Yeah, it's fine. I think nothing to worry. Nothing to worry.
Yes.
So it's all a part of the parcel. And
yes.
remember, if you are not understanding, means the conscious of not understanding itself is understanding.
Yes.
So yeah, with whatever spark you get through this event, definitely you can build a lot. Okay.
Yes. That is actually this motivation of this event.
Yes.
Sir, you can one thing participant asking if you can suggest them good books regarding quantum computing. Maybe in like next session you can share about some good literature link from the student can learn.
Yeah, definitely.
Yeah. Okay. Thank you, sir. Okay, participant, we are closing this session. Tomorrow again we will meet at 2 p.m. Yes, so just a minute. I want to present the certificate of appreciation to sir.
Thank you, ma'am.
Thank you so much. Thank you, ma'am.
Thank you, sir, for your invaluable contribution as a speaker for this course, Quantum Technology for Innovation and Startup. We deeply appreciate your dedication in sharing your profound knowledge, expertise, and insight on the topic, Introduction to Quantum Computing with Fundamental Application. Sir, I really appreciate your effort and engaging discourse, greatly enriched during the learning experience of all the participants. Thank you so much, sir. And we will see tomorrow again for further learning. Okay. Thank you so much, sir. Thank you.
Thank you, ma'am. Thank you.
Okay.
Thank you, sir.
Tomorrow meet at 2 p.m.
Yeah.
Okay. Thank you, sir.
Thank you, sir. Thank you.